What if I told you that every single AI breakthrough you have ever heard of, ChatGPT, self-driving cars, face recognition on your phone, all of it start with one tiny math equation? No, seriously, one equation. That is it. Hey, welcome back to the channel. This is episode 1 of our neural network fundamental series. Today we are cracking open the black box of AI and showing you exactly how a single artificial neurons learn to think. Stick with me till the end, because by the time this video is over, you'll be able to write your own neural network in just 30 lines of Python. Let's go. Here is something wild. ChatGPT has 175 billion parameters. Tesla Autopilot processes millions of images. Google Translate speaks over 100 languages, and yet they all run on same simple idea, an idea invented way back in 1957. You don't need a supercomputer to understand it. You don't need a PhD. In fact, you only need to understand one neuron. And once you get that, you understand all of AI. So, what is this magical idea? Let me show you. Here is exactly what you will master in the next few minutes. 1. How real neurons in your brain inspire the past artificial one. 2. The Perceptron, the simplest neural unit ever, and the bug that almost killed AI in the 60s. 3. How stacking neurons in layers solves problems a single one can't. 4. Activation functions, sigmoid, thon, relu. We'll show you which one to use and when. 5. And finally, we'll build a real neural network in Python from scratch. Just 30 lines. If that sounds good, smash that like button and let us dive in. Okay, story time. Back in the 1940s, scientists looked at the human brain and asked a question: can we copy this? Look at a real neuron. It has 3 parts, dendrites. These collect signals from other neurons. Think of them as inputs. The cell body, this adds up all those signals. And the axon, this spices up a signal only when the total is strong enough. Now look at artificial version. It does the same thing. Inputs come in. We'll call them x1, x2 and x3. Each input gets multiplied by weight. That is how important it is. We add them all up, and if the sum is big enough, boom, it fires. That's it. We literally turn biology into math. And that one trick, it changed the world. Alright, here it is. The equation that runs all of AI. Y equals f of sigma wi xi plus b. Don't panic. Let me break down in plain English. X is your input, like a piece of evidence. Y is the weight, how much that evidence matters. We multiply each input by its weight, then add them all up. That is the sigma symbol. Then we add a bias. Think of that as how easily the neuron gets excited. And finally, F, the activation function, squashes the answer into something useful. That is the whole thing: inputs, weights, sum, bias, and activation. 5 ingredients, 1 equation, the foundation of every AI on the earth. Now let us see in action with a real example. Imagine your friend invites you to a party. Should you go? Your brain rates 3 things. Is the weather good? Pretty important. Weight of 0.6. Are my friends going? Also important. Weight of 0.5. Is the party close by? Minor. Weight of 0.2. And you have got a built-in laziness threshold, a bias of negative 0.5. you need a good reason to leave the couch. Tonight, weather is great, that is a 1. Friends are going, another 1. But it is far away, that is 0. Let us compute 0.6 into 1 plus 0.5 into 1 plus 0.2 into 0 minus 0.5 equals 0.6 plus 0.5 plus 0 minus 0.5 equals 0.6. Is the 0.6 above 0? Yes. The neuron fires. Wait it. Go to the party. That's it. That is literally the entire perceptron. Now imagine doing this a few billion times. That is ChatGPT. But, and this is a big but, the perceptron has a problem, a better problem. Look at this. A single perceptron can only draw one straight line to separate things. For simple stuffs like and or logic, that works great. You can draw a line easy, but then there is a jar, exclusive or. Look at this picture. Can you draw one straight line that separates the green dots from red dots? Try it. Go ahead. Pause the video. You can't. It is impossible. This problem actually killed AI research for almost 20 years. People thought neural networks were a dead end. But then someone had a genius idea. What is the fix? Stack them. If one neuron can only draw a line, what if we use many neurons? And what if we put them in layers? Here is how it works. Input layer, your data comes in. Hidden layers, the magic middle where the network actually thinks. Output layer, your answer comes out. One layer draws a line. 2 layers can draw curves. 3 or more layers, they can carve any shape you can imagine. This is called a multilayer perceptron or MLP for short. Information flows left to right. Each connection has a weight, each neuron has a bias, and just like that, AI was back. So how does information actually move through the network? It is called forward pass, and it is just 3 steps repeated. Step 1, multiply and sum. Take the inputs, multiply by the weights, add the bias, same as before. Step 2, apply the activation. Cause the result through a non-linear function. We'll talk about why in a second. Step 3, pass it on. The output of this layer becomes the input for the next layer. Repeat, repeat, repeat until the very last layer spits out an answer. This is how a neural network thinks. It is just this little dance happening millions of times per second. Now I have to tell you something important. Without activation functions, deep learning literally doesn't work. Here is why. If every layer just does weight times inputs plus bias, pure math, then stacking 100 layers collapse into one big equation. A 100 layer network would be no smarter than a 1 layer network. Useless. But the moment you add a non-linear activation functions between the layers, boom, the network can suddenly learn anything. Curves, edges, faces, language, music, and anything. There is even a famous theorem from 1989, the universal approximation theorem, that proves in a neural network with just one hidden layer and a non-linear activation can approximate any continuous function on Earth. This is not exaggeration, that is math. That's why deep networks are so powerful. Okay, so which activation functions should you actually know? There are four big ones. Step function outputs 0 or 1, super simple, use it for teaching only, it is broken for real training. Sigmoid, that classic S-curve, outputs between 0 and 1, great for probability. Downside, it slows down landing in deep networks. Thorn, like sigmoid, but goes from -1 to +1. Centered around 0, used a lot in all the recurrent networks. ReLU, this is the king. ReLU stands for rectified linear unit. Sounds fancy, it is literally just if it is negative, make it 0, otherwise keep it. That's it, fast, simple, and 90% of the modern AI uses it. So which one do we use? Here is the cheat sheet. Eden aids use ReLU, it just works. ReLU giving you dead neurons, then try leaky ReLU or GELU. Binary yes or no output, use sigmoid. Multiple categories like classifying images, use softmax. Predicting a number like a price, use no activation or just linear. Building a fancy transformer like GPT, they use GELU or SWIGLU. This is the pro tip. Start with ReLU, match the output to your task, tune later, that is done. Okay, promise time. Let us actually build this thing. This is a neural network from scratch in Python, 30 lines, that's it. We import NumPy, we define ReLU, 1 line. We make a class called MLP with 2 layers. The weights are random, we multiply by 0.1 to keep them small so they don't explode. The biases start at 0. In the forward function, we do weights time, input plus bias, apply ReLU, then do it again for the next layer. Then we plug in some inputs and print the output. That is a working neural network right there. Reading the code, you already understood more about AI than 90% of the people. But wait, this network can predict, but it can't at land. That is coming in episode 2. Now in the real world, no one writes neural networks from scratch. Once you understand the math, framework like PyTorch and TensorFlow make it trivial. Look how short is this? PyTorch 4 lines, Keras 4 lines, same network, same logic. The framework handles messy stuff, matrix math, gradients, GPU acceleration. What is your job? Design the architecture, pick the layers, and train the model. That is the magic. You learn the hard way once, now we can fly. Here is the part that blew my mind when I first learned it. Each layer of a deep neural network learns something different, and it builds up like a pyramid. In a face recognition network, layer 1 sees just pixels, brightness values. Layer 2 combines pixels into edges and lines. Layer 3 combines edges into parts, eyes, noses, and mouths. Layer 4 combines parts into whole faces. Nobody programmed to do this. The network figured it out on its own. This is called feature hierarchy, and it is the secret reason deep networks crush shallow ones at hard problems. Alright, let us log this in. 5 things to remember forever. 1. A perceptron is just a weighted sum plus an activation. That is the atom of AI. 2. A single perceptron can solve linearly separable problems. Char breaks it. 3. Multilayer perceptron fix that by stacking neurons with nonlinear activations. 4. Without those nonlinear activations, depth is meaningless. The whole network collapses. 5. Remove for hidden layers, match the output activation to your task. That is the rule. Get those pi down and you understand the foundation of every AI system on the planet. Wait, I left out the most important part. How does network actually learn? Where do those weights come from? How does it know if it is right or wrong? That is episode 2, Backpropagation. The algorithms that made modern AI possible. Next time, we are covering gradient descent, how the network finds the perfect weights, the chain rule, the calculus trick that runs the world, why training is just rolling a ball downhill, and the two enemies of every deep network, vanishing and exploiting gradients. If you want that video the moment it drops, subscribe, hit that bell, and I will see you in episode 2. Until then, keep learning, keep building. ChatGPT can write your essays, Tesla cars can drive themselves, image generators can paint anything you describe, and every single one of them learned how to do the same way. There is one algorithm running underneath of all modern AI. It is not magic, it's not even new, it is from 1980s. But until you understand it, you don't really understand how machines learn. By end of this video, you will. Quick recap. In episode 1, we built a neural network from scratch. We took inputs, multiplied by weights, added them up, ran them through an activation function, and got a prediction. That is the forward pass. But here is what we never answered. Where did those weights come from? How does the network know whether they are any good? And when the prediction is wrong, which one of the millions of weights do you blame? That is what propagation answers. And once you see how it works, you will never look at the AI the same way again. Here is exactly what you are going to learn. First, loss functions, how a network knows it made a mistake. Second, gradient descent, the rolling ball trick that makes learning possible. Third, the chain rule, one calculus idea that powers whole thing. Fourth, backpropagation itself, how blame gets distributed across every weight. And finally, we'll write the actual code twice, one from scratch in NumPy and then again in PyTorch. Stay with me. Few minutes from now, you will understand something most AI engineers can't explain. Before we go deep on any one piece, look at whole picture. Every neural network on Earth, every one is trained with this exact 4-step loop. Step 1, the forward pass, push some data through the network, get a prediction. We covered this in episode 1. Step 2, compute the loss, compare the prediction to the truth, get a single number that says this is how wrong you were. Step 3, the backward pass, figure out for every weight in the network how much it is contributed to the mistake. Step 4, update the weights, nudge each one a teeny bit in the direction that would have been made the answer better. Then you did again and again and again millions of times. That's it. That is training. The rest of this video is just unpacking steps 2, 3 and 4. Step 2, measuring how wrong the network is. We need a single number. Why a single number? Because gradient descent coming up next only knows how to make one number smaller. There are dozens of loss functions out there, but 90% of the time you will use one of these two. On the left, mean square error, you use this when the network is predicting numbers, house prices, temperatures, stock prices. You take the difference between the prediction and the truth, square it, then average those square differences. pairing punishes big mistake way more than small ones, which is actually what you want. On the right, cross entropy loss. This one is for classification. When the network has to pick a category, cat or dog, spam or not spam, the math look scarier, but the intuition is beautiful. It punishes the network most when it was confidently wrong. If the model said, I am 90% sure this is a cat and it was a dog, the loss explodes. Punish overconfidence, that is the rule. Both of them produce one number. The whole training process is just one big game of trying to make that number smaller. Let me make this concrete. We are training an image classifier with 3 categories: cat, dog, and bird. The truth is, this image is a cat. Truth: 1 for cat, 0 for dog, 0 for bird. The network predicts 70% is cat, 20% is dog, and 10% is bird. Pretty good guess, but not perfect. Now let us compute the cross entropy loss. Step 1. Plug into formula -1 times log of 0.7 plus 0 times log of 0.2 plus 0 times log of 0.1. Step 2, and this is the elegant part, anything multiplied by 0 is 0, so those last 2 terms just vanish. We are left with negative log of 0.7. Step 3, punch into a calculator. The loss is 0.357, and here is what is beautiful. If the prediction had been 100% cat, perfect, the loss would be 0. If the prediction had been 1% cat, confidently wrong, the loss would shoot toward infinity. This number 0.357 is what gradient descent is going to attack next. It is going to drive it down toward 0. Okay, if you remember nothing else from this video, remember the next 30 seconds. Imagine the loss is a landscape, a curve like a valley. The horizontal axis is your weights, the vertical axis is the loss. How wrong the network is? We want to find the lowest value of that valley. That is where the loss is smallest. That is where the network is the best. Now here is the catch. We can't see the whole landscape. We are standing on side of it in the dark with millions of dimensions. We have no map, but we can feel which way is downhill, the slope under our feet. That is the gradient. And gradient descent is just this. Take a step downhill, recheck the slope, take another step, repeat. The formula on the right is the whole algorithm. New weight equals old weight minus step size times the gradient. The minus sign is the secret. The gradient points uphill. We go the opposite way. Every training step in every neural network ever built is doing exactly this. Now look at that step size, eta. It is just a number you pick, usually somewhere between 0.001 and 0.1, and it is the single most painful knob in all of deep learning. Pick it too small, like 0.0001, and the network crawls. Each step is so tiny you would need a million iterations to get anywhere. You will watch your GPU burn for 3 days and the loss won't budge. Pick it just right, say 0.01, and the network glides towards the answer, smooth, fast, and beautiful. Pick it too big, say 1.0, and the network goes berserk. It overshoots, it bounces, it explodes, your loss become none, your training crashes, and you wonder why you ever got into this field. This is the pro tip. Start at 0.01. If your loss explodes, halve it. If it crawls, double it. Or use Adam, a smarter optimizer that auto-tunes the rate. We'll cover that another day. Time for calculus. Don't run. There is only one rule you need. It is called the chain rule, and it is the entire mathematical foundation of backpropagation. Here it is. If a chain of things depends on each other, the rate of change ripples through the whole chain. You just multiply the rates together at each link. Look at the network. A weight W affects Z, which is the neuron's pre-activation. Z affects A, the activation output. A affects L, the loss. If I want to know how nudging W changes the loss, and that is exactly what I want for gradient descent, I just multiply how does L change with A times how A changes with Z times how Z changes with W. That's it. That is back propagation. Everything else in the next few slides is just applying this one rule very carefully, very many times. Here is how modern AI frameworks like PyTorch and TensorFlow actually do this. And the trick is genius. During the forward pass, the green arrows on top, the framework doesn't just compute the answer, it builds a graph. Every operation, every intermediate value gets recorded. Look at the example. X is 2, Y is 3, multiply them, get Z equals 6, apply ReLU, still 6, scale the difference from the target, get a loss of 16. All of those numbers are saved, cached, the graph remembers everything, then comes to backward pass. We start from the loss, the rightmost node, and walk the graph backward. At each step, we use the chain rule to compute the gradient. Then we hand it back to the previous node, which uses it to compute its own gradient, and so on. By the time we reach the input, every weight in the network has its own gradient, and we computed each one exactly once. That is the efficiency that lets backpropagation scale to billion parameter models. Let me derive backpropagation for one neuron. All the math right now, don't blink. On the left, the forward pass, 3 steps. Step 1, Z equals W times X plus B, weighted sum plus a bias. Step 2, A equals sigma of Z, apply the sigmoid activation. Step 3, loss equals A minus Y squared, squared error against the target. Now the question we want to answer, how does the loss change when I nudge W? Apply the chain rule, loss changes via A, then via Z, then via W. 3 derivatives multiplied together. Compute each one. The derivative of the loss with respect to A is just 2 times A minus Y. The derivative of A with respect to Z is the sigmoid times 1 minus the sigmoid, and the derivative of Z with respect to W is just X. Multiply them. Done. We now know exactly how to nudge W to make the next prediction better. Now scale up, same chain rule, but instead of one neuron, thousands of them organized in layers. 3 formulas do all the work, memorize them or don't, but
recognize them. First, the output layer, the error signal delta out is just the difference between prediction and truth multiplied by activation's derivative. This is the starting point, the seed of backpropagation. Second, hidden layers. Each hidden layer's error equals the next layer error pushed back through that layer weights, then multiplied by local activation derivative. That is the recursion. Output layer to last hidden to second to last, all the way back to the input. Third, the weight gradient. Once you have a layer errors, the gradient on its weight is just the error times the previous layer's activation and outer product. That is what we use to update. That is all of backpropagation. Three formulas, apply them in order, layer by layer.
Let us see all of this in action with concrete numbers. One training step, start to finish. Set up two inputs, 1 on 2, weights 0.5 and negative 0.3. Bias 0.1, target 1. Forward pass, Z is 0.5 times 1 plus negative 0.3 times 2 plus 0.1, which equals 0. Sigmoid of 0 is 0.5 and the loss, the squared error, is 0.25. Now the backward pass, the derivative of loss with respect to A is 2 times negative 0.5, that is negative 1. The derivative of A with respect to Z is 0.5 times 0.5, that is 0.25. Multiply the gradient at Z is negative 0.25. Then propagate to each weight. The gradient on W1 is negative 0.25 times 1, negative 0.25. The gradient on W2 is negative 0.25 times 2, negative 0.5. Weight update with a landing rate of 0.1. W1 becomes 0.525. W2 becomes negative 0.25. Bias becomes 0.125. And here is the magic. Every weight moved in a direction that would make the next prediction closer to 1, closer to the target. We didn't tell the network which way to move. The math told us. That is what learning is. Now for the dark side, backpropagation multiplies a lot of numbers together, and that is where everything can go wrong. There are two ways it involves effort. Vanishing gradients. If your gradients are smaller than 1, say 0.2, and you multiply 5 of them together, you get a 0.0032. Multiply 20 of them and the gradient is essentially 0. Your early layers stop lining, they get no signal, the network gets stuck, and you can't tell why. Exploding gradients, the opposite problem. If your gradients are bigger than 1, say 5, and you multiply 5 of them, you get over 3000. 20 of them, you will see infinity. Your loss becomes none, training crashes, and you cry. This is why deep learning was stuck for decades. Training network with more than 5 levels was nearly impossible. Then around 2012 to 2015, a few Q fixes changed everything. ReLU activations, better weight initialization, batch normalization, residual connections, and gradient clipping. Suddenly, networks with 100 layers or 1000 become trainable, and modern AI was born. Time to see the code, the entire algorithm, 30 lines of Python. At the top, we define the sigmoid activation and its derivative. two one-liners. Then we initialize two weight matrices randomly, small numbers multiplied by 0.1, so the activation don't explode on the first pass. Inside the training loop, forward pass two lines, compute the hidden layers, then the output layer, then the loss. Backward pass the chain rule written out, then again for the previous layer. 6 lines that compute every gradient in the network. Update 2 lines, subtract gradient times the learning rate. That's it. This is the entire algorithm that powers GPT, that powers stable diffusion, that powers AlphaFold. Scale it up to billions of parameters and few hundred GPUs, and you have got an modern AI. Now here is the same network in PyTorch, and watch what happens. We define the model, same architecture, two linear layers with sigmoid. We pick a loss function and an optimizer. In the training loop, predict, compute loss, and zero the gradients. And then this one line loss dot backward, that single function call does everything we just wrote by hand. It walks the computational graph backward, it applies chain rule at every node, it computes every gradient for every weight in the network. All those derivatives we computed manually, AutoGrad just does them. Same algorithm, different boilerplate. And now you know what is happening underneath. Most AI engineers using PyTorch today have no idea. You do. Let us lock it in. Three things to remember forever. 1. Loss measures how wrong the network is, just one number. 2. The gradients points uphill, so we go the opposite way, that is gradient descent. 3. Backpropagation is just the chain rule applied carefully layer by layer from loss back to the input. If this video helped a concept finally click for you, hit like. Tells YouTube to show this to other people who need it. If you want episode 3 orbiting regularization and dropout, hit subscribe. It drops next. And if you have a question, anything you didn't get, anything that surprised you, drop it in the comments. I read everyone. Now you know how networks actually land. I will see you in episode 3.
You try the network, the loss went down, beautifully down. You hit 99% on the training set. You celebrated. Then you tested it on real data. 60%. What happened? Your network didn't learn. It memorized. And memorizing is not learning. Today we fix this. By the end of next few minutes, you will have 5 tools that turn brittle memorizing networks into ones that actually work in the wild. Here is the quick recap. Episode 1 and 2 gave us everything we needed to build and train a neural network. We had the architecture, we had backpropagation, we had gradient descent, we had a network that could learn, and it worked. The training loss dropped to nearly zero. But here is the problem nobody warned you about. The validation loss told a different story. It dropped at first and then it climbed back up. The network was getting better at the training set and was at everything else. This is the hard truth. A model that aces the training set is not the model that works. It is a model that cheated. Today's job is to stop that cheating. 5 tools, each one solves the problem from a different angle. Here is what we'll cover. First, bias versus variance. The fundamental trade-off behind every machine learning problem. You will never look at a model the same way again. Second, L1 and L2 regularization. Penalize big weights. Force the network to be simpler. Third, dropout, the wild 2012 idea that randomly disables neurons during training, and some more. This makes the network better. Fourth, early stopping and data augmentation, the cheap, easy techniques that almost no one talks about but everyone uses. And finally, the code. We'll add 3 lines to a PyTorch model and watch it actually generalize. By the end of this video, you'll have a real ML engineer toolkit for fighting overfitting. Before we attack overfitting, we need to know it's just a problem. Every machine learning model is a fight between two enemies. Enemy number one, high bias, also called underfitting. The model is too simple, it can't capture the pattern in the data. Symptoms, both training and validation loss are high. The model is too rigid, it is drawing a straight line through the curves. What is the fix? Make the model bigger, more layers, more neurons, more capacity. Enemy number two, high variance, overfitting. The model is too complex. It memorizes the training set instead of learning the pattern. Symptoms, training loss is low, validation loss is high. The model is too flexible. It is trying a wiggle through every single point, including the noise. What is the fix? That is today's whole episode. Regularize. The goal is speed spot. Is a model just complex enough to capture the pattern, but not so complex that it memorizes noise? That is what every ML engineer is hunting for every time on every project. This is the chart. If you take only one image away from this video, take this one. You look at this chart every time you train a model for the rest of your career. Let me walk you through it. The green line is your training loss. It goes down smooth, always going down because the network keeps fitting the training set tighter and tighter. The red line is your validation loss, performance on data the network has never seen. It goes down at first, then it bottoms out, then it climbs back up. The growing gap between green and red is the visual definition of overfitting. The network is getting better at memorizing and worse at generalizing at the same time. And the lowest point of the red curve is your best model. That is where you should have stopped training. We'll back to this idea. It is called early stopping and it is free. Same data, 3 different models. Look at what each one does to it. On the left, underfit a straight line through every data. The model is too simple to even see the pattern. It is missing the cause entirely. In the middle, just right, the line follows trend without chasing every noisy bump. This is the model that will work on new data. On the right, overfit, the line wiggles through every single point, even the noise. It got 100% on the training set, but it's learned the noise as if it were the signal. On the new data, it will be a disaster. Today's job is to stop the network from becoming the third one. Now, you might be thinking, why is overfitting such a big deal for neural networks especially? Why don't simple models like linear regression have this problem the same way? 3 numbers tell the story. 175 billion. This is the parameter count of GPT-3. More weights than English words ever spoken in human history. 10 to negative 6. That's a typical sample to weight ratio in deep learning. Each training point has to teach a million weights how to behave. And here is the wild one, 100% is if you take a big enough neural network and give it completely random labels that don't follow any pattern at all, it will still fit them perfectly. It will achieve 100% accuracy on pure noise. That tells you something important. Neural networks are not naturally good at finding patterns. They are naturally good at compressing data into their weights. Regularization is what forces them to find the actual pattern instead. First weapon, the simplest one, L2 regularization, also called weight decay. Here is the formula. Final loss equals original data loss plus lambda times the sum of scared weights. We are adding a penalty to the loss function based on how big the weights are. Lambda is the strength knob, typical values between 0.001 and 0.1. Bigger lambda means a harder push towards smaller weights, which means a simpler model. Sum of W squared is just every weight in the network squared then added together. Squaring is important. It punishes big weights way more than small ones. A weight of 5 contributes to 25 to the penalty. A weight of 0.5 contributes only 0.25. What is the effect? The optimizer gets two competing forces. One pulls the weights towards whatever value fit in the training data. The other pulls them towards 0. Result is weights stay small unless they are really useful. This technique is so universal, it is literally the default in every modern deep learning framework. Every PyTorch optimizer has a weight decay parameter. Every network you have ever heard of, GPT, BERT, ResNet, uses some form of L2. L1 looks almost identical to L2, but the difference is profound. Same idea, analyze the size of weights, but instead of squaring them, we just take the absolute value. Why does this matter? It is all about the gradient. When you take the derivative of L2 penalty, you get 2W. That is a force proportional to the weight. Big weight, big push towards 0. Small weight, tiny push. Result is weights get smaller and smaller but never quite reach 0. When you take the derivative of L1, you get a sign of W, just plus or minus 1, regardless of how big or small the weight is. It is a constant push. And that is the magic. Small weights get the same push as big weights. Eventually, the constant push shows them all the way to 0. They become exactly 0. Result, a sparse model, many weights become exactly 0, meaning the network has automatically decided some inputs are not useful and just turn them off. The network does its own feature selection. So, which one should you use? The honest answer, almost always L2. L2 is the universal default. It is used in every modern deep learning model, ResNet, BERT, every transformer. It is the silent default in every PyTorch optimizer. If you don't know which one to pick L2. Use L1 when you specially want sparsity. Two cases, you want a smaller, faster model. L1 will zero out useless weights so you can prune them. Or you want interpretability, you want to know which input features the model actually cares about. And yes, you can use both at the same time. It is called elastic net. But honestly, most people just use L2 and move on with their lives. Now for the technique that sounds completely insane when you first hear it, and it became one of the most important breakthroughs in deep learning history. In 2012, Intern's lab proposed something bizarre. On every training batch, randomly delete half the neurons in your network. Yes, really, each batch you flip a coin for every neuron. Heads, the neuron contributes. Tails, you set its output to 0. The probability, usually called P, is typically zero point 0.2 to zero point 0.5. Sometimes you really do delete half the neurons and the network gets better. Why does this work? Three reasons. One, process redundancy. No single neuron can become indispensable because it might be deleted on the next batch. So every important feature ends up being detected by multiple neurons. Second, approximate ensembling. Each batch is essentially training a different subnetwork. By the end, you have trained an exponential number of models, all sharing the same weights. At testing, they work together. 3. Break co-adaptation. Without dropout, neurons can form precise cliques. Groups that work together perfectly but fall apart if any one piece is missing. Dropout prevents these cliques from forming. Here is what dropout looks like in practice. There are two modes. On the left, training mode. All the hidden neurons have red X through them. They are disabled for this batch. The network is paused to make do with the what is left. On the right, test mode. All neurons turned back on. The full network is active. There is one little subtle during training when you delete all the neurons. The surviving neurons need to be scaled up by a factor of 1 over 1 minus p, so the expected output stays the same. PyTorch handle this automatically. You don't have to think about it. Now my favorite technique, because it is the simplest and most underrated and completely free. Early stopping. It is exactly what it sounds like. Stop training before the model starts overfitting. Remember the chart from earlier? The validation loss goes down, hits a minimum, and then climbs back up. The minimum is your best model. So here is the algorithm. After each epoch, measure the validation loss. If it is the lowest I have seen, save a copy of the model. If the validation loss has not improved in n epochs, that is called patience. Stop training. Use the saved best model. That's it. No new math, no extra layers, no tuning. Just save your best model and kit while you are ahead. Use it on every project. That is literally no downside. One last technique, and honestly, the most powerful one of all when it works. More data is the best regulator in the universe. If you double your training set, your model will be generalized better almost always. But getting more data is expensive, so when you can't get it more, you pick it. Data augmentation is the art of generating new training samples from existing ones. One image becomes 8. Take the original, rotate it slightly, flip it horizontally, crop a corner, brighten it, add a little noise, shift the colors, mix it with another image. All 8 versions are still valid examples of the same class, but to the network they look like 8 different training samples, and the network can't memorize 8 versions as easily as one. Same idea works for any domain. For text, synonym replacement, random word selection, back translation. For audio, time stitching, pitch shifting, adding background noise. There is an augmentation playbook for every domain. Always cheaper than collecting more data, often just as effective. Time for the code. Both L2 regularization and dropout from scratch in about 30 lines of NumPy. L2, the loss is 2 extra lines. Compute the data loss as usual. Then add lambda times the sum of scared weights, that is the new loss. When back propagation hits this, the gradient picks up a 2 lambda w term for each weight, that is the weight decay, force pulling weights towards 0. 2 lines, done. Dropout is 3 lines. If we are training, generate a random binary mask the same shape as the activations, multiply the activations by the mask that zeroes out the drop neurons, then divide by 1 minus p to scale up the survivors. If you are not training at inference time, just return the activations unchanged. The whole technique, 3 lines. And here is the beautiful part. Both techniques can be added to any model architectures without changing anything else. No re-engineering, no special design. That's why they are universal, because they just plug in. And in PyTorch, 3 keyword arguments. Dropout, add NN dot dropout as a layer in your model. Done. L2 pass weight underscore decay equals 1 e minus 4. When you create your optimizer, done. Mode switching, call model.train. Before training, and model.eval before inference. PyTorch handles the dropout, train or test logic automatically. This is the important rule. Always remember to call eval before inference. If you don't, dropout will still be active and your predictions will randomly worse every time you call them. It is a classic bug, hits everyone once. 30 lines of NumPy become 3 keyword changes, same algorithm, same effect, different boilerplate. Now the playbook, different problems need different tools. Here is how working ML engineers actually decide. Validation loss climbing, early stopping, free, instant, always do this first. Default new project L2 weight decay, set it to 1A minus 4. It is the universal baseline, cost you nothing. Deep network, 10 layers or more, add dropout, be between 0.2 and 0.5. This is the standard for CNNs, MLPs, transformers, basically every modern architecture. Limited training data, data augmentation, cheaper than collecting more, often just as effective. Want a smaller model? L1 zeros out, useless weights so you can film them. Modern transformer or LLM, all three drop out. L2 augmentation. This is the industry standard. And the golden rule is start simple, add one technique at a time, measure. Bigger is not better, more regularization is not same as better regularization. Take a moment, 3 episodes ago, a neural network was a black box that did magic. Now you know what is inside, all of it. Episode 1, Foundations, Perceptron, multilayer networks, activation functions, the forward pass. Episode 2, Landing, loss function, gradient descent, the chain rule, backpropagation. Episode 3, Generalizing, bias and variance, L1 and L2, dropout, early stopping, data augmentation. From Perceptron to production, you now understand the entire pipeline that powers every modern AI systems on Earth. If this series helped you, hit like, it tells YouTube to show this to other people who need it. Subscribe for more deep dives. There is a lot we can build together, and drop a comment telling me what you want to cover next. I read every comment, and what gets the most votes is the what gets made. Thanks for going through series with me. I will see you in the next one. Pick up your phone, look at the camera. It knows your pace in less than a second. A self-driving car is moving at 60 miles per hour. It reads a stop sign, then a speed limit, then another car tail lights, all while moving. How? How does a computer see a picture and understand what is in it? The answer is one idea, just one, called convolution. By the end of this video, you'll understand it completely and you will know exactly how every camera, every photo app, and every self-driving car works on the inside. First, why don't regular neural network works for images? We learned how neural network work in the last series. So, why do we need a new kind? 3 reasons, all bad. Reason 1, too many parameters. A normal photo is 224 by 224 pixels, that is 50,000 pixels per color channel. If you connect every pixel to every neuron in the next layer, you need 150 million weights. For one image, it won't fit on your computer. It won't train. It is hopeless. Reason 2, a regular network doesn't know where an image is. If the cat is at the top of the picture, the network learns cat at the top. If the same cat moves to the bottom, the network thinks it is totally different image. Same cat, different position, confusing network. Reason 3, regular networks ignore where pixels are. They take your image, flatten into a long line, and treat each pixel as separate. Nearby pixels lose their meaning. Edges disappear, shapes disappear, texture disappear. So we need something better, a network designed around how images actually work. That something is convolution. Here is what we'll cover today. 5 things. First, convolution, the single math operation behind all of computer vision. After this video, you'll never forget what it is. Second, filters and pooling. How a network learns to spot edges, shapes and objects without anyone telling it what to look for. Third, the architecture pattern, the recipe that every CNN follows. Once you see it, you will see it everywhere. Fourth, a quick history, 30 years of breakthroughs in 60 seconds from the first working CNN in 1998 to today's model. And fifth, the code will build a working image classifier in PyTorch, 30 lines, real code. By the end, you'll able to build your own. Now, the heart of the video, what is convolution? Forget the word, it sounds scary, it is not. Convolution is just 3 steps repeated millions of times. Step 1, take a small grid of numbers, maybe 3 by 3. We call it a filter. Think of it as a tiny pattern detector. It might be designed to spot a vertical edge or a horizontal edge or a corner. Doesn't matter for now. Just imagine a small grid with some numbers in it. Step 2, slide that filter over your image. Start at the top left, move it 1 pixel to the right. Then again, when you reach the right edge, drop down a row and start over, like reading a book, left to right, top to bottom. Step 3, at each position, multiply filter values by image values underneath. Then add up all those products into single number. If the number is big, the filter found its pattern. If it is small or 0, the pattern is not there. That is the formula at the bottom. Don't memorize it, just remember the words. At each position, dot product the filter with patch underneath. Slide, multiply, add, repeat. That is convolution. Let me show you a real example. It will make everything click. On the left, a tiny pi by 5 image. The sine squares are 1, the dot square are 0. Notice the picture has a clear vertical edge in the middle where dark left side meets bright right side. In the middle of filter, it is 3 by 3 grid. Red square have negative ones, black squares have 0, green squares have positive 1. This filter is designed to spot vertical edge. Look at the pattern. The left column is negative, the middle is 0, the right column is positive. So if there is a dark to bright transaction going left to right, this filter will fail. Now we start with the filter in the top left, sitting on the dash square yellow. Multiply each filter cell by image cell underneath, add it all up. The math is at the bottom, 0 times negative plus, plus 0 times 0, plus 1 times 1, and so on, all the way through 9 numbers. The total is 3, a big positive number. The filter detected its vertical edge here, and that is the value that goes into top left of the feature map on the right. Now look at the whole feature map. All 3 are stacked on the left. Why? Because the vertical edge in the input goes top to bottom on the left side of the image. The filter found the edge at every row. That's it. That is convolution. Slide, multiply, add, and repeat. Now, here is the magical part. We don't write the filter values by hand. In real CNNs, the network learns the filter values from data, just like any other weights in a neural network. The filter that detect edges, the filter that detect cores, the network figures them out by itself, and it's get better. When you stack many convolutional layers, each layer learns a different level of feature. The early layers, first or second, they learn simple things. Vertical edges, horizontal edges, diagonals, color blobs, just basic shapes. The middle layers, 3, 4, and 5 combine those edges. They learn corners, curves, simple textures, patterns, things made of edges. Then deep layers, 6, 7, deeper, combine those parts. They learn eyes, wheels, ears, whole faces, whole objects, and here is the wild thing. Nobody told the network to learn this hierarchy. Edges in early layers, shapes in middle, objects deep down. The network figured out from data all by itself. We just gave it pictures and labels. The hierarchy emerged. Two more concepts before we move on. Stride and padding. Think of them as knobs that control how big the output is. Stride is how many pixels the filter jumps. If the stride is 1, the filter moves 1 pixel at a time. the output stays roughly the same size as the input. If the stride is 2, the filter jumps 2 pixels each time. The output is half the size. It is faster but less detailed. Stride 3 or more, really aggressive. Use only when you want to shrink the image fast. Padding is something else. When the filter slides across the image, it can't go past the edges, so the output gets smaller by 2 pixels on each side for a 3 by 3 filter. After many layers, your image sinks to nothing. So what is the fix? It is nothing but padding. Add a ring of zeros around the edges of the image before convolving. Now the filter can reach all the way to the corners. The output stays the same size. We'll call this same padding. It is the most common setting in modern CNNs, and there is a formula at the bottom. Output size equals input size plus 2 times padding minus filter size divided by stride plus 1. Don't memorize it now, just know it exists. When you design a CNN, you will use this formula to figure out exactly how each layer output will be. Now the second piece of CNN puzzle is pooling. Convolution detects features, pooling makes the detections robust to position. Here is how it works. Take a 4 by 4 grid of activations, divide into 4 2 by 2 quadrants. You can see them in different colors on the screen. From each quadrant, take just biggest value, throw away the other 3. We call this max pooling, and it makes output 4 times smaller. So why do we do this? There are 3 reasons. 1. Translation invariance. If the cat moves a few pixels to the right, the maximum value barely changes. The network answer stays stable. It learns to recognize cat regardless of position. 2. Smaller maps. 4 times fewer pixels to process means faster training and less memory. After 3 pooling layers, a 2 to 4 by 2 to 4 image becomes 28 by 28. 3. Robustness to noise. Tiny pixels changes get smoothed out. Only the strongest signals survive. Convolution detects features. Pooling make them. Those detections survive small changes. Together they are unstoppable. Now let us put all together. Every CNN follows the same recipe. Look at the pipeline at the top of the screen. Input image goes into the left, then convolution, then ReLU. That is the activation function from the last series. Then pooling. Repeat that pattern. Convolution, ReLU, pool, convolution, ReLU, pool, convolution, ReLU, pool. After several rounds, we flatten the feature maps into a long vector. Then we feed it into a regular dense layer, just like networks from episode 1 of the last series. Finally, softmax gives us probabilities for each class. Notice the two halves. The first half, all those convolution ReLU pool blocks, is the feature extraction. The network is learning what is in the image. The second half, flatten plus dense plus softmax, is classification. The network is deciding what the image is. 2 patterns to remember. First, spatial dimension shrink. The image started 2224 by 2224. After one pool, 112 by 112. After 2 pi 6 by pi 6, and so on, smaller and smaller. Second, channel depth grows. The input is 3 channels, red, green, blue. After the first convolution layer, maybe 64 channels. After the next 128, after the next 256. More and more abstract features. On the right is VGG16, a famous real CNN. Notice how the dimensions follow exactly the pattern. Spatial, size ops, channel double. Every CNN you will ever see follows this recipe. Quick concept: why do CNNs need to be deep? It comes down to one idea: receptor field. How many pixels of the original image one neuron sees? Look at the first picture, layer 1. A single neuron in this layer sees a 3 by 3 patch, just 9 pixels, just enough to detect an edge. Layer 2, now each neuron sees a bigger area around pi by 5, 25 pixels, enough for a corner, a simple shape. Layer 5 and beyond, each neuron sees a use patch over 100 pixels in each direction, enough to see entire objects, faces, animals, whole scenes. This is why we go deep. Each layer combines the patches below it deep enough and a single neuron sees the whole image. That is how CNNs go from this pixel is bright to this is a cat. Quick history 5 architecture that defined computer vision 1998 LeanNet, the first working CNN built by Anne. It read handwritten zip codes for the post office. Tiny by today's standards, only 60,000 weights, but it worked. Then nothing for 14 years. CNNs were no. Researchers played with them, but they didn't work well at scale. The world used other methods for vision. 2012 AlexNet, built by Alex and Ilya in Intern's lab, it crushed every competitor at the ImageNet context. 60 million weights, ReLU activation trained on GPUs. The deep learning era starts here. 2014 VGZ and Inception. The big idea, go deeper. VGZ add 19 layers, 138 million weights. Crazy at the time, it worked. 2015 ResNet, the biggest jump in years. What is the trick? Skip connections. They let networks be 150 layers deep and still trainable on every benchmark for the next 3 years. 2020 and beyond, Vision Transformers, a new approach borrowed from language models. They beat CNNs at use scale, but more on that in a few minutes. Notice the pattern. Each generation went deeper, 5 layers, 8, 19, 152. The breakthroughs were not a new idea, they were tricks that made deeper networks trainable, ReLU, GPUs, skip connections. I want to slow down on 2012 because what happened there was the biggest moment in modern AI. Look at the numbers. Before 2012, the best computer vision systems got 26% error on ImageNet. There is a contest where you have to identify what is in a picture with 1000 possible categories. 26% error was the best in the world, achieved by handcrafted feature detectors and traditional machine learning. Decades of careful research. Then in September 2012, AlexNet entered the context and won with 16% error, a 10% point leap overnight from a CNN trained on a couple of consumer GPUs. Today, deep CNN and transformers get under 5% error, better than humans on most categories. Here is why this changed everything. Before AlexNet, computer vision researchers spent decades handcrafting feature detectors. They wrote code to look for edges, corners, textures. Years of work for tiny improvements. AlexNet learned all of that automatically, better than human could design. From data, within 3 years, every major tech companies shifted to deep learning. Google, Facebook, Microsoft, Apple, Tesla, all betting their futures on this one technique. The same idea spread to speech language biology. AI, as we know today, is the consequence of one CNN that worked in one weekend in 2020. Time for code, convolution from scratch, 15 lines of NumPy. I'm not going to read every line. I put out the 3 key parts. First, the output size formula. Right where you see out underscore h and out underscore w. That is exactly the formula from earlier. Input size plus padding minus filter size divided by stride. Just turn into code. Second, the double for loop, 2 nested loops. The outer one goes through every output row. The inner one goes through every output column. Together, they cover every position the filter slides to. This is the heart of the algorithm. Third, the convolution itself. Look at the one line highlighted in green. Output equals sum of patch times kernel. Patch time kernels element-wise multiplication. Sum at the malloc. That is the entire operation. Below the function, a real example. We define a vertical edge detector. Negative ones, 0, positive 1. 3 rows of that pattern, then we run it through our function. We get back a future map showing where the vertical edges are. Convolution from scratch, 15 lines. That is the whole map. Now let us see how you write a real CNN in PyTorch. Forget from scratch version. In production, you don't write convolution by hand. You compose layers like Lego blocks. Look at the structure. We define a class called simple CNN inside two parts. The feature extractor, those convolution, ReLU, pool blocks, and the classifier, flatten plus, dense plus output. 3 convolution blocks, each one takes the input, applies a 3x3 filter with same padding, then a ReLU action, then 2x2 max pool, just like recipe we just talked about. Notice how the channels grows from 3, that is RGB, to 32 in the first block, then 64, then 128. Channels double, spatial dimension half. Standard CNN pattern. After 3 pools, the 32 by 32 input image is now 4 by 4. We flatten it, pass it through a dense layer. Add some dropout for regularization and output 10 logits, 1 per class. That is complete image classifier, about 30 lines, trains on CAFR 10, a dataset of 50,000 small images across 10 categories in under an hour on a regular GPU. That is what working ML engineers actually write. Image classification was just the beginning. The same convolution building blocks for everything in vision. Object detection. Don't just say what is in the image. Find and locate every object. Draw boxes around them. Models like YOLO, Faster, or CNN do it here. Every self-driving car uses this. Every security camera. Every photo app that tags your friends. Semantic segmentation. Classify every single pixel. This pixel is road. This pixel is car. This pixel is sky. Models like UNet, DeepLab, segment anything. Used for medical imaging, separating organs in a CT scan. Satellite analysis, identifying buildings and crops. Photo editing, separating the foreground from background automatically. Generation, generate brand new images that never existed. GANs, stable diffusion, tally. All the AI art you have seen on the internet, these models, all powered by convolution underneath. 3D vision, reconstruct a 3D screen from 2D images used in AR and VR. Autonomous robots, virtual production for movies. All of these tasks, all of them powered by same convolution we learned today. Now, an honest question, are CNN still the best? Around 2020, a new architecture appeared, vision transformers or VITs. They borrowed the transformer architecture from language models and they became for vision. The story is not transformer 1, it is more interesting. CNNs have built-in knowledge about images, translation, invariance, locality, spatial structure. They start with right bias. They work well even on small datasets. They are fast at lower resolution. They are mature and easy to deploy. What is their weakness? They struggle to look at whole image at once. They build up context layer by layer and they don't scale beyond about 600 million parameters efficiently. Vision transformers are the opposite. They look at the whole image at every layer. They scale beautifully to billions of parameters. They use the same architecture as language models, which is great for combining vision and text, but they need massive data, 10 million images at minimum. They are slow on small images and they need a lot more compute. So who wins? Both. For most production applications, image classification, object detection, segmentation, CNNs are still the practical choice. For frontier scale research and foundation models, VAEs win. And the latest trick, modern hybrids like Connext and Spin transformers combines both. The best vision models in 2026 use convolution and attention. Best of both worlds. So, which architecture should you use? Here is the honest playbook. Standard image classification, ResNet or EfficientNet. mature, fast, and pre-trained weights per frame. Object detections are segmentation, YOLO per detection, unit per segmentation, both CNN based, still rule for this task. Medical imaging are satellite, specialized CNNs, limited data plus strong spatial structure equals CNN territory. Frontier scale research, building a foundation model, vision transformers. If you have millions of images, they scale further. Mobile or edge deployment, mobile net or efficient net, designed for low parameters and low latency. And if you don't know it, start with ResNet 50, the default, solve 80% of vision tasks. What is the golden rule? Start with the pre-trained ResNet, fine-tune, measure, only move to fancier architecture if you actually need to. Bigger is not better, what works is better. Now you know how missions see. Three things to remember forever. One, convolution. A small filter slides over an image, multiplying and summing. That is the entire operation. Everything else built on this. Two, hierarchy. Early layer detect images, middle layer detect pods, deep layer detect objects. Nobody designed this. The network learned it from data. Three, pooling downsample activations adds robustness together with convolution, makes network see space the way humans do. Next episode, we move from space to time, RNNs, LSTMs, and GRUs, how network process sequences, text, speech, sensor readings. CNNs see space, RNNs see time. Subscribe so you don't miss episode 2. I will see you in the next one. ChatGPT writes a paragraph. It guesses every next word based on every word before it. Your phone hears "Hey Siri" in the middle of your sentence. It picked apart the sound of your voice, one teeny piece at a time. Spotify predicts the song you like next based on the order of every song you have ever played. How? Last episode we learned how machines see. Today we learn how they remember. By the end of this video, you will understand exactly how every voice assistant, every translator, and every text generator works on the inside. Episode 1 gave us CNNs. CNNs are amazing at images. So why do you need another architecture? 3 reasons, all are bad. Reason 1, no order. Look at these 2 sentences. Dog bites man versus man bites dog. Same 3 words, completely different meaning. A CNN treats input as a fixed grid. Swap 2 words and the network see the same thing. It doesn't understand the order. Reason 2, pixel length. A tweet has 20 words. A novel has 200,000. Real world sequences come in every length, but CNNs need every input to be the same shape. You can't process any length with a pixel size network. Reason 3, no memory. When you read a sentence, the 100 word depends on the first one. Music depends on the notes that came before. Stock prices depend on entire trading history. Regular networks have no way to remember anything from earlier inputs. Each input is processed alone. So we need something better, a network that process one element at a time and remember what came before. Here is what we'll cover 5 things. First, the RNN idea, a network with a memory loop, the simple powerful concept behind everything else in this video. Second, why simple RNNs fail, the vanishing gradient problem, and why it nearly killed sequence learning in the 90s. Third, LSTM and gates, the breakthrough that solved long-term memory, 3 little gates that changed the AA. Fourth, GRUs, a simpler, faster cousin of the LSTM when you don't need all the machinery. And fifth, the code will build a working text generator in PyTorch 30 lines. By the end, you know exactly how to build one yourself. Here is the entire idea behind RNNs. It is almostly embarrassingly simple. On the left of the screen, a regular neural network, input goes in, hidden layer, process it, output comes out. Like the networks from last series, no memory between different inputs. On the right, an RNN, same input, same hidden layer, same output. But notice the golden arrow at the top, the hidden layer connects back to itself. That's it, that is the only difference. We added one loop and it changes everything. Now When a new input arrives, the hidden layer doesn't just process the input, it processes the input plus its own previous state. The network remembers. Look at the equation at the bottom. H underscore t equals tan of w underscore x times x underscore t plus w underscore h times h underscore t minus 1 plus b. Don't be scared by the symbol. It says new memory equals a function of the current input and the previous memory. Mix the new one with the old. That is all an RNN does. Let us open RNN cell 3 operations. That is whole thing. Step 1. Take two inputs. The current input, let us call it x underscore t. That could be today's world or this second's audio sample or today's stock price plus the previous hidden state h underscore t minus 1. That is everything the network remembers from before. Step 2. Multiply and add. Multiply the input by a weight matrix w underscore x. Multiply the previous memory by a different weight matrix w underscore h. Add them together. Add a bias term. Standard neural network math. Step 3. Squash and output. Pass the result through a tan activation function. This squeezes the value 2 between -1 and +1. That is your new hidden state. Use it for prediction, then pass it forward as a memory for the next time step. That is the whole RNN 3 matrix operation and a tan function. Repeat once per time step and welcome to sequence learning. Here is the usual that makes RNNs click. We unroll the loop. Instead of drawing one cell with a loop, we draw one copy of the cell for each time step side by side like flipping through a movie. Look at the bottom row. Inputs. The sentence is the cat sat on the. 5 words, 1 word at each time step. X underscore 1 is the, X underscore 2 is cat, and so on. Middle row, the RNN cells H underscore 1, H underscore 2, H underscore 3, H underscore 4, H underscore 5. Each one is the network memory at that point in time. Notice the gold arrows between them. Each cell passes the hidden state to the next. Memory flows forward. Top row outputs. At each step, the network make a prediction. What is the next word? Or is this a noun? Or what is the sentiment? Same network applied 5 times. Here is the key insight people miss. It is still one network. The weights are shared across all 5 copies. We just draw it, unroll to see what is happening. By time step pi, the network has seen whole sentence. It can make a prediction that depends on everything before. How does an RNN learn? Backpropagation through time. Don't let the name scare you. It is just a regular backpropagation applied to the unroll network. Step 1. Forward. Run the input sequence through the unroll network. Get an output at each step. Compare to target. Compute the loss. Same as any neural network. Step 2. Backward. Propagate gradients backward through the same unroll network. The gradient flows from time step 5 back to 4, back to 3, back to 2, back to 1. Like backpropagation in a regular deep network, except the depth is the number of time steps. Step 3. Update. Here is the trick. The same weights were used at every time step. So we sum the gradients across all time steps, then apply standard gradient descent. One weight matrix update using gradient signal from all 5 steps. Now here is where it all goes wrong. The same weight matrix W underscore H is multiplied at every time step. For a 100 step sequence, the gradient passes through W underscore H 100 times, and that is a problem. Simple RNNs work great for short sequences. For long sequences, they completely fall apart. Here is why. Look at the curve on the screen. The vertical axis is gradient magnitude, how strong the learner signal is. The horizontal axis is time steps. On the right, when time equals 1 or 2, the gradient is strong. The network lands fine for recent inputs. But look what happens as you go further back. The curve drops past by time step 15. The gradient is essentially 0. The network can't learn from the distant past. The math at the bottom shows why. The gradient at step t is proportional to weight matrix raised to the tth power. If the weights are smaller than 1, this goes to 0 past. If they are larger than 1, the gradient explodes instead. Either way, it is a disaster. In practice, a vanilla RNN reading a 100-word sentence forget the first words completely by the end. Translating a paragraph impossible. The network can't connect pronoun back to its subject 50 words earlier. By the late 1990s, researchers thought RNN were a dead end. Then in 1997, two researchers proposed a fix so elegant it kept RNNs alive for next 20 years. The long short-term memory cell LSTM for short. The core idea is one sentence. Add a separate memory highway, a path for information to flow forward without being multiplied at every step. If the gradient doesn't pass through a weight matrix, it can't vanish. That highway is called the cell state, written as C_T. It is the network long-term memory. Information enters it, information leaves it, but mostly it just flows forward, barely modified, like a conveyor belt running through the network. An LSTM also keeps regular hidden state H_T, same as RNN, the working memory used for prediction at each step, and it has 3 gates: target, input, and output. These decide what to remember, what to learn, what to share. We'll see them in the detail next. Each gate is a tiny neural network. It outputs a value between 0 and 1. Think of it as a percentage. 0 means block completely. 1 means left it all through. 0.7 means keep 70%. Gate 1, the target gate, decide what to throw away from the memory. Imagine reading she said S, then a new sentence start. He looked away. The subject changed from she to he. The target gate decide keep she or throw it out and replace with he. Gate 2, the input gate, decide what new information to add to memory. New subject just appeared. Important, save it with high weight. New unimportant word like the, low weight, don't waste memory on it. Gate 3, the output gate, decide what to share from memory right now. Predicting the next word. Only output the parts of memory that matter for this prediction. Keep the rest hidden but available for later. 3 small networks that decide what to remember, what to learn, what to share. All learn automatically from data. Nobody programmed the rules. The network figures out by itself when to forget she and when to keep it. Here is exactly how an LSTM process one-time step. 4 steps. The 4 steps that power Google Translate for years. Step 1, forget. Multiply the old cell state by the forget gate. If the forget gate says 0.9, we keep 90% of the old memory. If it says 0.1, we throw most of it away. Step 2, input. Propose what new information to add. Compute a candidate update, a vector of potential new memories. Pass it through tan function to keep it bounded. Step 3, update. Add new information into cell state. Notice we are adding, not multiplying. This is the trick that fixes vanishing gradients. Multiplication shrinks, addition doesn't. Step 4, output. Run the cell state through tan function, then multiply by the output gate. The result is our new hidden state H_T used for prediction at this step and passed to the next cell. The cell state goes through multiplication at the forget gate and addition at the update step. Addition doesn't shrink gradients. That is the entire trick. That's why LSTM solve vanishing gradients. That's why they work where simple RNNs fail. LSTM are powerful but heavy. 3 gates, cell state, hidden state, lots of parameters. Do we need all that? In 2014, researchers proposed a simpler version, the Gated Recurrent Unit (GRU). Two changes from LSTM. First, merge cell state and hidden state. GRUs just have one memory variable, not two, simpler and faster. Second, only two gates instead of three. A reset gate decide what to forget, an update gate decide how much new information to add. The forget and input gates of LSTM get merged into one update gate here. What is the result? About 25% fewer parameters, about 25% faster to train. Performance is usually within 1 to 2% of an LSTM, sometimes worse, sometimes better, depends on the data. When to use which? Default to GRU. It is the practical choice. Switch to LSTM only if you have very long sequences, more than 100 steps, where extra cell state really helps. Quick reference table, 3 architecture side by side. Memory handling vanilla RNN has just one hidden state. LSTM has hidden state plus a cell state highway. GRU merges them into one. Gates RNN none. LSTM 3 forget input and output. GRU 2 reset and update. Vanishing gradient RNN yes. Patel blah. LSTM and GRU solved. Parameters RNN is the baseline. LSTM has about 4 times more. GRU has about 3 times more. More parameters means more memory and slower training. When to use each in 2026? Vanilla RNN almost never. Too limited. LSTM long complex sequences where memory matters. GRU the default. Use it unless you have a specific reason not to. From 2014 to 2020, LSTM and GRUs powered nearly every sequence AI product you used. Many still do. Speech recognition, Siri, Alexa, Google Voice, turning audio wave into text one teeny piece at a time. Bidirectional LSTM was the workhorse of years before Transformer took over. Machine translator, read a sentence in English, output it in French. Encoder decoder LSTM ran Google Translate for billions of people from 2014 to 2017. Then attention came along and the Transformer architecture started taking over. But for 3 years, LSTM translated the entire internet. Music and text generation, predict the next note, predict the next character, predict the next word. Andre Choropathy Care RNN blog post in 2015 launched many ML queries. If you ever wanted to generate text, you probably started with an LSTM, time series and sensors, sensor reading, stock prices, weather data, factory machinery health. LSTMs find patterns across time. The case study in episode 3 uses exactly this. Real factory sensors, real LSTM model and real money saved. Time for code, RNN from scratch, 20 lines of NumPy. I won't read every line. 3 things to notice. First, the weights, 3 matrices, W_X, transform the input, W_H, transform the previous hidden state, B is the bias, that is the entire learnable state of RNN. We initialize them randomly, scaled down by 0.01 to keep gradient stable. Second, the one-step update, look at the step mentioned, one line of math, H equals tan of W_X times plus W_H times plus B, same formula as slide B, that is what runs at every time step. Third, unrolling through time, look at the forward method, we loop over the sequence, call step at each input, each call uses previous hidden state automatically because it is stored in sub.h, that is the recurrence in 20 lines of Python. Now let us see how you would actually write an LSM in production. PyTorch. Forget from scratch version. In real code, you don't implement the gates yourself. PyTorch handles that math. You just compose layers. Look at the structure. We defined a class called text LSTM, 3 components. An embedding layer turns each token into dense vector. Why? Because LSTM work with vectors, not raw ID numbers. The embedding is landing during training. It's figure out what the should be look like as a 128 dimensional vector. The LSTM layer itself, one line RNN.LSTM with embed dim and hidden dim, PyTouch handles the gates, the cell state, all of it. Two stack layers for more capacity, drop out between them. For regularization, same idea as fundamental series episode 3. A linear projection maps the hidden state back to vocabulary probabilities. Softmax gives us the probability of each next token, that is complete character level text generator. Train it on Shakespeare, generate Shakespeare, train it on Python code, generate Python code, 30 lines. This is the architecture that defined sequence AI from 2014 to 2017. Honest question, are RNNs still used only in 2026? In 2017, Transformer paper came out. By 2020, LSTM had been retired from most state-of-the-art sequence tasks. GPT, BERT, Claude, all are transformers. So why are we even teaching RNNs? Because the story is not Transformers 1, it is more interesting. RNNs and LSTM still have real strength. They process one step at a time. Nature for streaming data. Their memory footprint is constant per step. It doesn't grow with sequence length. At small scale, they are often faster than transformers. Smaller models, faster inference. What is their weakness? They can't parallelize training across time steps. Each step depends on previous one. Transformer process whole sequence in parallel, that is huge speed advantage when training on billions of examples. Transformer win at scale, billions of parameters, foundation models, anything where you need raw quality and you have the compute. RNNs win for streaming, time series, embedded systems, edge devices, anywhere memory is tight, latency matter, and data flows one element at a time. And there is a plot twist in 2024, state-space models, Mamba, S4, revived the current approach. They beat Transformer on some long sequence benchmark. RNNs are back. The story keeps unfolding. Now you know how machines remember. 3 things to remember forever. 1. Recurrence. A loop from output back to input. The hidden state at time t depends on input t and state t minus 1. That is all sequence learning is. 2. Gates. LSTM solve vanishing gradients with 3 gates for gate, input and output plus a cell state highway. Information flows forward almost untouched. 3. GRE is simpler, 2 gates instead of 3, about 25% faster. The default choice when you don't need long range memory. Next episode we get practical. Episode 3, AI in predictive maintenance, real factory data, real LSTM model, real memory saved. Most ML channels teach theory. This case study show what happened when you actually deploy it. If this video helped, hit like. It tells YouTube to show this other people learning from same things. Subscribe so you don't miss episode 3. I will see you in the next one. $50 billion, that is the cost of unplanned battery downtime every year worldwide. A single bearing fails, a production line stops, hundreds of thousands of dollars vanish. Every hour the line is down. Multiply by every factor on earth, that is 50 billion. But here is the thing. Most of those failures could be predicted days in advance, sometimes week, with sensors, with code, with one LSTM model, exactly like one we built in episode 2. Today I am going to show you exactly how real factory, real data, real money is saved. Most ML videos teach theory. This one shows what happens when you actually deploy it. Every factory in the world picks one of 3 ways to maintain a machine. 2 are terrible. One is what we will build today. Way 1, reactive, run it until it breaks. When something fails, you fix it. Cheap until it is not. One failure can take $1 million production line down for days. Emergency repair, loss output, angry customers. This is the old way. It is still how most small factories work today. Way 2, preventive, replace parts on a schedule. Every 90 days, swap the bearing. Doesn't matter if it is healthy, better than reactive but blind. You throw away parts that still have life left, and you have still missed failures that happen between schedule changes. Way 3, predictive, use sensors, use machine learning, predict the failure before it happens, replace the part 1 week before it dies. No wasted parts, no surprise downtime. This is the holy grail of industrial maintenance, and it's what we are building today. Here is what we'll cover: 5 parts in order. First, the setup, meet ACMC bearings, the factory, the machine, the cost of failure. Second, the data, what sensors actually capture, what failure looks like in raw signals. Third, the model, why an LSTM beats XGBoost here, and the exact architecture we used. Fourth, the results, confusion matrix, ROC curve, the precision recall trade-off in real money terms. And fifth, the business impact, downtime prevented, dollars saved, and the lessons we learned the hard way, including mistakes that nearly killed the project. Let me introduce you to ACMC bearings. It is a composite case based on real predictive maintenance deployments. The numbers are real, the factory is realistic, name changed to protect everyone. ACMC makes heavy duty bearings, 3 plants, 20 production lines, 48 CNC machine centers, about $120 million in annual revenue. Mid-sized manufacturer, solid, profitable and growing. But they have a problem. Every year they lose $2.4 million to unplanned downtime. Let me break that down. 8 to 12 major failures per year. Each one cost about $200,000. Average line downtime 36 hours per failure. That is a day and half of zero output plus cost of emergency repairs, expedited parts and wartime labor. Our goal, predict bearing failures 7 to 14 days before they happen, cut unplanned downtime by 70%, save ACMC over $1 billion a year. Every modern CNC machine has sensors. Most factories don't use them. Wheel, 6 channels sampled continuously. Let me show you what each one tells us. Vibration sampled at 10,000 times per second. The number one indicator per bearing wear. Early micro cracks in the bearing shows up here weeks before any human could notice. Temperature 1 reading per second. Failing bearings run hot. A 5 degrees Celsius rise above baseline is a warning sign. Simple but powerful. Motor current 100 times per second. Worn bearings need more torque to spin. Current draw goes up sometimes week before the failure. Spindle RPM, we compare what machine was commanded to do versus what it actually did. A drift between two means mechanical resistance via acoustic microphone at 44 kHz. Bearings make distinct sounds as they fail. High frequency clicks and grinds human can't hear. Algorithm can. And finally, oil analysis. A lab sample once a day. Metal particles in the oil means something in airing drawn. Direct evidence but slow to collect. 6 sensors, 6 perceptives on the same machine. The model gets to see all of them at every moment in time. Here is most important slide in this video. What does a bearing failure actually looks like in sensor data? On screen, you are looking at vibration data from real CNC spindle, 14 days, 3 pages. Each page tells a story. Page 1, healthy, days 14 down to 7. Look at the green line, small, regular waves. This is normal vibration. The bearing is fine, has been for months. Page 2, early warning, days 7 down to 2. Look at the gold line. The amplitude is twice what it was. New frequencies start appearing. If you are not looking carefully, you would miss it. Most humans do. Page 3, failing, last 2 days. Look at red line. Vibration is everywhere. Wild, chaotic. Now anyone can see it, but it is too late. The line will be down within hours. A human can spot failure usually by day 2, but the early warning at day 7, subtle, hard to catch. That is exactly where machine learning wins. Before we can train a model, we need label data. This sensor pattern leads to failure in n days. Here is how we build the dataset. Step 1, raw sensor logs. 18 months of historical data, 48 machines, 6 sensors each. About 2.5 terabytes of raw data. Most importantly, 23 confirmed bearing failures during that period, each one carefully documented by the maintenance team. These are our positive samples. Step 2, sliding windows. We chop the timeline into 1 hour snapshots. Each window contains the last hour of all 6 sensors. We slide forward 10 minutes at a time. Vibration gets down sampled from 10 kHz to 100 Hz. Still plenty of signals, way less data. Total about 75,000 windows. Step 3, labels. Here is the simple rule. If a window is within 14 days of confirmed failure, label it as class 1, failing. Everything else class 0, healthy. Result is wildly imbalanced. 92% is healthy, 8% failing. We'll fix that with weighted loss. Critical detail, we slip train, validation and test set by machine, not randomly. Random slips leak data between sets and implant accuracy. We learn this hard way, more on that later. Raw vibration data is noisy. We extract features, numbers that have physical meaning. The LSTM see patterns more clearly this way. Two kinds of features, time domain and frequency domain. Time domain features statistical summaries of raw signal, RMS, root mean square, measures overall energy. Peak to peak catches sudden impacts. Kurtosis measures spikeness. Early failures spike often. Crest factor and screwness round out the picture. Frequency domain features run an FFT, fast Fourier transform, on the vibration signal. This breaks the signal into its component frequencies. Why does this matter? Because bearings have specific failure frequencies. BFFO, ball frequency, frequency outer race, tells us about outer race defects. BPFI tells us about inner race. BSF tells us about rolling elements. If energy start showing up at these specific frequencies, we know exactly what is failing and where. Total 47 features per sensors, 6 sensors, 282 feature per timestamp fed as sequence to LSTM. We didn't just pick LSTM because we said in episode 2. We tested 4 model families. Here is exactly why the LSTM won. Baseline 1, logistic regression, F1 score 0.42. Average lead time barely over a day. Too simple, no memory of past time steps. Each window judged in isolation, useful only as a baseline to beat. Baseline 2, random forest, F1 0.68. Lead time almost 3 days, decent. Random forests are great with engineered features, but they still treat each window independently. They don't see how features evolve over time. Baseline 3, XZ-Boost, F1 0.74. Lead time 3.5 days. Strong baseline, the best tree-based result, still missing time evolution though. Then LSTM F1 0.87, lead time 8.4 days, more than double the warning of XZ-Boost. Why? Because LSTM sees how feature evolve over time. It catches degradation that is invisible in every single snapshot. 8 days of warning, that is enough time to schedule replacement during planned downtime. Game changer. Here is the actual model architecture. not a single LSTM. A carefully designed stack that handles real-world messiness, missing data, varying machine types, class imbalance. Input shape: each sample is a sequence of 144 time steps, that is 24 hours of data at one sample every 10 minutes. Each time step has 282 features. First layer, batch normalization. Why? Our sensors have wildly different scales. Vibration is in the thousands, temperature is in tens. Without normalization, the model would obs over vibration and ignore temperature. Batch norm fixes that. Then two stacked LSTM layers. First layer has 128 units and returns full sequence, so the second layer can see everything. Second layer has 64 units and returns only last hidden state. That last state summarizes the whole 24-hour history into 1 hectare. Dropout between layers 30%, prevent model from memorizing specific machines. If a particular spindle has a wide vibration signature, we don't want that model learning that spindle, we want it learning that pattern. Final, dense layer with sigmoid activation. One output, probability of failure in the next 14 days. Total parameters about 260,000. Training time 2 hours on a single A100 GPU. Small enough to fit on Raspberry Pi for inference. Time per code. This is the real training pipeline. I won't read every line. 4 things to notice. 1. Batch norm post. Look at forward pass. We transpose, normalize, then transpose back. Necessary because PyTorch batch norm 1D expects feature in dimensional 1, not 2. 2 LSTM stacked. First layer returns full sequence. Second layer takes only last hidden state. That last state is our summary of everything that happened in the past 24 hours. 3. Weighted loss. Look at the POS underscore weight. We set it to 92 divided by 8, about 11.5. What does this do? It tells loss function. Every failure example matters 11.5 times more than every healthy example. Without this, the model learns to always predict healthy, because that is right 92% of the time. Useless. The weighted forces it to take failure seriously. 4. Gradient clipping. Clip to norm equal to 1. LSTM can have exploding gradients during training. Clipping keeps training stable. Without this, you will see your loss randomly spike and your model diverge. 6 months of held out test data. 8 machines the model had never seen before. Here is how it performed. Look at the confusion matrix on screen. 4 cells, each one tells you something different. Top left, true negatives, 5124 healthy windows correctly classified as healthy. Boring but important. If this number were low, you would be drowning in false alarms. Top right, false positives, 84 false alarms. Times the model said failing, but the bearing was fine. We'll come back to this in a second. Bottom left, false negatives, 13 missed failures. The model said healthy, but the bearing failed. These are expensive mistakes. We want this number as close as 0 as possible. Bottom right, true positives, 120 correctly caught failures. Each one is money saved. The 4 key matrices, precision. 57% of our alerts were real failures. Recall, we caught 90% of all real failures. F1 score 0.87. Average lead time 8.4 days of warning. Now 57% precision sounds bad. It is not. Let me explain why on the next slide. Every machine learning model has a knob. How confident must it be before raising an alert? Setting that knob is a business decision, not a math one. Look at the chart on screen. 3 curves. The horizontal axis is the threshold from 0.1 on the left to 0.9 on the right. The vertical axis is cost per month in thousands of dollars. The gold curve, false alarm cost, it drops as the threshold goes up. White high threshold means few alerts, few false alarms, low cost. The red curve, missed failure cost, it rises as the threshold grows up. White high threshold means we miss real failures. Each one cost $200,000. The black curve, total cost, the sum of both. It has a minimum somewhere in the middle, that is the optimal threshold. For us, it is 0.35, total cost $85,000 per month. Here is the trade-off in plain numbers. Each false alarm cost us $8,000. Inspection time, loss output. Each missed failure cost us $200,000. Line down for 36 hours. What is the ratio? One missed failure equals 25 false alarms. So we accept lots of false alarm to never miss a real failure. That's why our precision is 57%. It is not a bug, it is the right answer. After 12 months in production, these are real numbers. What changed at ACME bearings? Unplanned failures before 10 per year, after 2 per year, down 80%. Unplanned downtime before 360 hours per year, after 60 hours, down 83%. Maintenance cost before $2.4 million per year, after 640,000, down 73%. What is the bottom line? We saved ACME $1.76 million annually. Project cost $280,000. 6 months of work, 2 engineers. Payback period 8 weeks, not 8 months, not 8 quarters, just 8 weeks. That is what predictive maintenance actually delivers when you do it right. Trying the model was about 20% of the work. Getting it running reliably on a factory floor, that is other 80% is. The deployment has 3 tiers. Each tier does one thing. Tier 1, the factory floor, the edge. Sensors stream data to a Raspberry Pi sitting next to each machine. The Pi buffers raw data, computes engineered feature locally, RMS Cortesis FFT, then runs LSTM inference every 10 minutes, outputs a probability of failure. Tier 2, the cloud, raw data and predictions get sent to a AWS as JSON. S3 stores raw data about 2.5 terabytes per year. Timescale DB logs every prediction once a month. An Airflow pipeline retrains the model on SageMaker using fresh data. Updated model gets pushed back to all edge devices over the air. Tier 3, alert and action. When prediction crosses 0.35 and stays above for 3 consecutive readings, we triggered an alert. Y3 consecutive eliminates blocky single shot false alarms from sensor noise. Alert creates a ticket in ServiceNow, sends an SMS to on-call engineer and lights up a dashboard. Then human inspects, confirm and fixes. 8, inference matters. When the factory internet goes down, and it will go down, predictions still run locally, alerts still fail, the system never goes dark. Here are the 4 mistakes we made and what we would do differently. Mistake 1, inflated validation accuracy. Our initial F1 score was 0.94. When we deployed to production, it dropped to 0.61. What happened? We slipped train and test sets randomly across all data. The same machine appeared in both. The model memorized specific machines, not failure patterns. Peaks slipped by machine, different machines in different sets. Now we measure generalization, not memorization. Mistake 2, data drip kill the model. Month 3 in production, model performance dropped 30%. Why? ACME switched raw materials. New material caused a slightly different vibration baseline. The model tried on old data didn't generalize. Peaks monthly retraining plus drip monitoring. Alert team when input distribution shift. Mistake 3, alert fatigue. Week 1, the maintenance team ignored 60% of alerts after first 3 were false alarms. Even though those were not really false alarm, the team had lost trust. Peaks had severity types. Show the model confidence, show which sensor triggered, trust require transparency. Black box prediction didn't get acted on. Mistake 4, rare failure model missed. 23 failures in training data covered only 4 distinct failure modes. Some rare models, like cake failures, were never seen during training. Model couldn't detect them when they happened in production. Peaks, synthetic data augmentation. Physics simulators like Modelica generate rare failure signature we don't have example of. LSTMs were the workhorse from 2018 to 2024, but the field is moving. Here is where it is going and what you should actually learn next. Direction 1, foundation model for time series, Kronos, Time GPT, Lag Llama. These models are pre-trained on millions of time series datasets. You fine-tune on your sensors. Result, 10 times less labels data needed. Use for project like ours where label failures are rare. Direction 2, transformers for sequence, Informer, Patch DST, Autofarmer, attention mechanisms now beat LSTM on long forecasting horizons. If you need to predict weeks ahead rather than days, these are the architecture to use. Direction 3, explainable AI, tools like sharp integrated gradients, attention visualization. Maintenance team need answer, not just probabilities. Why did the model alert? Which sensor triggered it? What patterns did it see? Explainability is now critical for adoption. Direction 4, digital twins plus ML. Physics inform neural networks, combine physics simulation of bearings with ML. Train models on synthetic players we have never actually seen in real data. Solves the rare failure mode problem. That's a wrap. Advanced architecture complete. 3 episode, 1 journey. Episode 1, CNNs. How machines see convolution, filters, hierarchical feature. The architecture that made computer vision work. Episode 2, RNNs and LSTM. How machines remember recurrence, gates, memory highways. How network process sequences and time. Episode 3, this one. How machines predict real factory, real LSTM, real $1.76 million saved. Theory meets engineering reality. Thank you for watching this series. I will see you in the next one. Hey, and welcome back. This is episode 1 of our series on transformers and large language models. Today we are going to unpack one single idea, attention. It sounds simple and at its heart it is, but this one idea is the engine behind every modern AI model you have heard of. By end of this video, you'll understand exactly how it works and you'll even be able to do math by hand. Let us get into it. Read this sentence with me. The animal didn't cross the street because it was too tired. Now, quick question. What does the word it point to? The animal or the street? You know right away. It is the animal. Streets don't get tired. But stop and think about how you know. Your brain quietly looked at every other word in the sentence and decided which ones mattered. That act, picking what to focus on, is the attention. And teaching a machine To do that one thing is what open door to modern AI. By end of today, you'll able to compute attention by hand, read the math without fear, and write it into code. So, why all the fuss? Back in 2017, a research paper came out with a bold title: Attention is all you need. And that name was the point. The authors threw away the older, slower parts of these models and kept only attention. It worked beautifully. Today, every big AI model you can name, the ones that try, chart, and answer your questions, is built on same idea. And here is the neat part. With attention, any word in a sentence can reach any other word in a single step. Older models had to pass information word by word, like a long game of telephone. Attention skips all that. To see why attention was such a big deal, let us look at what came before it. Older models read a sentence and try to squeeze its whole meaning into small box of numbers. Then they used only that box to write the output. That is fine for a short sentence. But for a long one, the box just is not big enough. Details followed. The ending of sentence pushes out the beginning. It is like trying to remember a whole paragraph after reading it once. So fast. Attention fixed this. Instead of one frozen box, the model gets to look back at every word, whatever it needs to, and decide, rush each time which words to lean on. Here is the whole idea in 3 small steps. For each word, the model does this. First, it compares, it asks, how much does each other word matter to me right now? And gives each one a score. Second, it cleans up those scores so they turn into neat weights that add up to 1. Think of it like splitting 100% of your focus across the words. Third, it blends. It mixes the words together using those weights, more from the important ones, less from the rest. Here is an everyday way to picture it. Imagine searching a library. Your question is what you are looking for. Each book's label on the spin tells you what is inside. You match your question against the labels, then pull the most from the books that fit best. That is attention. Let us give those 3 things their real names: query, key, and value. Every word gets turned into these 3 little numbers list. The query is what a word is looking for. Picture the word it asking, who am I talking about? The key is what each word offers in return. A word like animal raises its hand and says, pick me if you need something to point to. And the value is the actual information that gets passed along once a match is made. So the query goes shopping. The keys are the labels on the shelf, and the values are what you take home. The model learns how to build all 3 on its own just from reading lots of text. Now let us look at the famous formula. Don't worry, we'll take it apart piece by piece, and you will see it is friendlier than it looks. First piece, we multiply the queries and keys together. This just measures how well they match. A bigger number means a better match. Second piece, we shrink those numbers down a little by dividing them. This keeps the math stable. We'll see why in a moment. Third piece, softmax. That is just a fancy name for turn these scores into clean weights that add up to 1. Last piece, we multiply by the values. That is the final blend. The weighted mix we talked about, and that is the whole formula for small moves. Let us actually do with real numbers. 3 words, the cat and set. Our query is the word cat. It is asking which words should I pay attention to. Step 1, the RAM match scores. The gets a 2, cat gets a 6, sat gets a 1. So cat matches itself the most, makes sense. Step 2, we scale those down a little to keep things steady. 6 becomes 3, 2 becomes 1, and so on. Step 3, softmax turn them into focus and look what happens. About 82% of the attention lands on the cat itself. A small slice goes to the and a tiny bit to set. We just computed attention by hand. That's all it is. Two quick details that makes this work in practice. First, why do you shrink the numbers? Because when numbers have lots of feature, the math scope can get really big. And when they get too big, softmax goes all or nothing. It picks one word and ignores the rest, which makes learning hard. Shrinking the scores keep things smooth and pay. Second, why softmax at all? Because it gives us exactly what we want. Every weight is positive. They all add up to 1 and bigger score gets a lot more focus. Best of all, the model can choose to focus sharply on one word or spread its focus across many, and it learns which to do. When all the queries, keys, and values come from same sentence, we'll call it self-attention. Every word looks at every other word, including itself. This grid shows it. Each row is one word, and the bright space shows what it is paying attention to. Look at the row per set. It lights up under cat. The model has quietly learned that web sat goes with the subject cat. And nobody taught it any grammar rules. It picked that up just from examples. It is a clever upgrade. One round of attention can only spot one kind of link at a time. So why not run several at once? That is multi-head attention. We run a few copies side by side. These are called heads. Each head has its own way of looking. One might track grammar, another might track meaning, another might track word order. Then we join all their answers together and blend them into one. More heads, more kinds of patterns caught at the same time. There is one catch we need to fix. Attention looks at all words at once. Like ingredients dumped into a bowl, it doesn't naturally know the order they came in to it. Cat sat cat look the same. So we add a little signal to each word that marks its position, first, second, third, and so on. We build these signals out of simple repeating waves like the ones on screen. Some wiggle slowly, some quickly. Mixed together, they give every position its own fingerprint so the model can tell where each word sits. Let us see it in real code. Don't worry about memorizing this, just follow along. We start with queries and keys and we multiply them to get the math score. Then we shrink those scores to keep things steady. There is an optional step for hiding certain words. We'll use that in later episode. Next, softmax turn the scores into clean weights. And finally, we multiply the values to get an answer. That is the whole thing about 11 lines. Everything else in these chain models is built on top of this small block. Now, here is the multi-head version wrapped up neatly. In the setup, we create the pieces we need, the parts that build queries, keys, and values, plus one to blend the heads at the end. Then, when data comes in, we build the queries, keys, and values, slip them across the heads, and run the same attention step we just wrote. After that, we join heads back together and do one final mix. Notice we are reusing the exact function from the last slide. Once you understand one head, you understand them all. Remember a puzzle from the start. Let us see how the model handles it. Look at the row for the word it. Most of its attention falls onto animal. Exactly the answer you gave in the first minute of this video. The model was not given any grammar rules. It learned to connect it with animal purely from reading. And here is the big takeaway. Things like this, figuring out what a word points to, linking far apart words, even following a line of reasoning, all of it grows out of this one simple blending step stacked over and over. Before we wrap up, A quick map of the main types you'll run into. Self-attention is when a sentence looks at itself. That's the one I have been doing. Cross-attention is when one sentence looks at another, handy for things like translation. Casual or masked attention hides future word, so the model can't peek ahead. That is how text generators write one word at a time. And there are two ways to measure match between words. The past modern way uses simple multiplication, that is the standard today. The older way used a tiny extra network, same goal, different tool. Let us be honest about the trade-offs. On the plus side, any word can reach any other in one step. It runs fast because it can do a lot of work at the same time. The attention weights even let us peek at what the model is looking at. And the same trick works for text, images, and sound. On the downside, the cost grows quickly as sentences get longer, double the words, and the works goes up 4 times. Very long documents get expensive. It needs that extra position signal we added, and it needs a lot of data to learn well, powerful but not free. So where does the leave us? We can now explain attention as simply choosing what to focus on. You can read that scary formula and know what each part does. You can work out the weights by hand, and even you have seen the code that makes it real. Next time in episode 2, we'll show you how this one building block turns into famous models like BERT, GPT, and even models that you look at pictures. If this helped it click, give it like and subscribe so you don't miss the next one, and tell me in the comments what should it pay attention to next. See you in episode 2. Welcome back. This is episode 2 of our series on transformers and large language models. Last time we cracked open attention, the trick that lets a model decide what to focus on. Today we put that trick to work. We'll meet 3 famous families of models: BERT, GPT, and Vision Transformer. They look very different on the outside, but underneath they all run on same idea. Let us see how. Quick recap. In episode 1 we learned attention and we stacked it into a repeatable unit called a transformer block. Think of that block as a single Lego piece. So here is today's puzzle. If everyone is using the same Lego piece, why do these models feel so different? One understands text, one writes text, one looks at pictures. The answer is simple, and it is the key to this whole episode. They arrange the same block in different ways and they train it on different games. That's it. Same piece, different builds. Let us look at 3 main models. There are 3 ways to arrange the block. The first is an encoder. It reads the whole input at once and try to understand it. This is what BERT uses. The second is decoder. It writes from left to right, one word at a time. This is what GPT uses. And the third is both together, an encoder paired with a decoder. It reads one thing and writes another, which is perfect for jobs like translation. Notice the little arrow on each word. They show what each word is allowed to look at. That tiny difference is what we'll zoom into next. Here is the part that surprises people. BERT and GPT use the exact same attention math. The only big difference is what each word is allowed to look at. On the left is BERT's way, bidirectional. Every word can see every other word both before and after it. So the word sat can look at the, cat, and down all at once. Full context, great for understanding. On the right is GPT's ways, casual. Each word can only see the words that came before it. So sat can see the and cat, but it's not allowed to peek at down. Why block it? Because when you're writing, you don't get to see the future. You have to guess the next word from what you have written so far. That blocking is exactly what makes a model able to generate text. So see everything and you understand. See only the past and you can write. Let us start with BERT. The name stands for bidirectional encoder, representations from transformers. But don't worry about that mouthful. In plain words, BERT reads whole sentence at once, looking in both directions to really understand it. Here is the important thing. BERT doesn't write text. Instead, it turns words into rich number summaries. We call them embeddings that other tools can use. Think of BERT as a careful reader who hands you a deep understanding of sentence rather than a writer who talks back. So how does BERT get so good at understanding? Through a simple game called fill in the blank. You take a sentence, hide one word, and ask the model to guess it. Because BERT can see the words in both sides, it makes smart guesses and puts most of its confidence on the best bit. Now do this billions of times across huge amounts of text. To fill in those blanks well, the model is forced to learn how language fits together, grammar, meaning, the works, and it learns all of it without anyone labeling a thing. So where do you actually use BERT? Anywhere you need to understand text rather than write it. Classification, like deciding if a review is positive or negative, or if an email is spam. Search and ranking, matching a question to the best answer. Finding names, pulling out people, places, and dates from a block of text. And embeddings, tuning text into numbers so you can measure how similar two pieces of writing are. If the job is about understanding, sorting, or judging, BERT and its cousins are strong choice. Now let us meet GPT. The name stands for Generative Pre-trained Transformer, and GPT does one thing astonishingly well. It predicts the next word, then it does it again and again. Because it only looks to the left at what is already been written, it can just keep going, add a word, use that to pick up the next word and repeat. String enough of those together and you will get full sentences, paragraphs, and even code. This is the family behind ChatGPT and most of the chat assistants we have used. GPT's training game is just as simple as BERT. Give it some word and ask what comes next. Give it the cat and it learns to predict sat. Now feed the cat sat back in and it predicts on. Feed that back in and it predicts the. See the pattern? It writes one word, then reads its own writing to choose the next one. That loop, predict, add, repeat is the entire idea played across whole internet's worth of text. It is enough to teach a model to write about almost anything. So GPT shines wherever you need to create something, chat and assistance, answering questions and holding back and forth, writing and summarizing, drafting emails, stories or short summaries, writing code, turning a plain English request into working code, and a neat trick called few shot. Show GPT just a couple of examples of what you want and it picks up pattern and keep going. If the job is about generating, GPT is your tool. Let us put them next to each other so it sticks. BERT is an encoder, GPT is a decoder. BERT reads both direction, GPT reads left to right only. BERT learns by filling in the blanks, GPT learns by predicting the next word. BERT's strength is understanding, GPT sees generating. You will find BERT style models powering things like church. You will find GPT style models powering chatbots. Same engine pointed at two different goals. Here is where it gets fun. For years, images were handled by different kind of model. Then researchers asked a bold question: what if we treat a picture like a sentence? The trick is chop the image into small square patches, line those patches up in a row like words, and feed them to the very same transformer. No special image machinery, just patches as words, and surprisingly it works really well. This is called Vision Transformer. Let us walk through it in 3 steps. Step 1. Cut the image into a grid of small patches. Step 2. Treat each patch like a word in sentence. We line them up, add a little position info so the model knows where each patch sat in the picture, exactly like word order in text. And we add one more special marker at the front to summarize the whole image. Step 3. Feed that row of patches into same transformer we have used all along, and out comes a label like cat. So picture quietly becomes a sequence of patches and attention works on it exactly the same way it works on words. Should vision transformers replace older image models called RNNs? Not always. Each has its place. A vision transformer sees the whole image at once, so it is great at linking far apart parts of picture, and it scales beautifully when you have tons of data. The catch is that it needs a lot of data to shine. The older RNNs looks at small local areas first, works well even with less data, and it is very efficient. Its weakness is that it can miss big picture connections across an image. So lots of data and big picture understanding lean toward vision transformer. Less data or limited compute, a CNN is still a fine choice. Let us see how easy this is actually used. With a popular pre-library called Geek-based transformers, you can load a ready-made BERT model in just a few lines. Here we ask for sentiment model, give it the sentence. This tutorial made attention finally click, and it tells us sentiment is positive with very high confidence. We didn't train anything, we just borrowed a model someone already trained and put it to work. Using GPT is just as simple. We load a small GPT style text generator, give it the start of sentence. Attention is powerful because, and ask it to continue. The model writes the next words for us one at a time, just like we saw earlier. A little setting, let us add some creativity so it doesn't always say the same thing. Same library, same few lines, but now we are generating instead of understanding. Using a vision transformer is just as simple. We load a small image classifier, hand it a picture, here a photo of cat, and ask the model what it sees. Behind the scenes, it slips the image into patches and pay attention to the ones that matter, just like we saw earlier. One little setting asks for top 3 guesses, and the model hands back a label and how confident it is. Same library, same few lines, but now we are feeding it images instead of words. Let us make this practical. Here is a quick guide for picking a model. Need to understand sort or search text, reach for BERT style encoder. Need to write chart or generate, reach for a GPT style decoder. Working with images, a vision transformer or a classic CNN will fit. And if you're turning one piece of text into another, like translating, an encoder decoder is built exactly for that. Match the shape of model to shape of your problem and you're halfway there. So what would we gain today? You can now explain how one transformer block becomes an encoder, a decoder, or both. You can tell BERT and GPT apart by how they read and how they are trained. You understand fill in the blank versus predict the next word. You have seen how an image turn into patches for a vision transformer, and you can pick the right family for a given task. Next time in episode 3, we get hands-on prompt engineering and fine-tuning. That is how you get great results from these models, both by asking them well and by teaching them with your own data. If this made things click, a like really helps, and subscribe so you don't miss it. See you in episode 3. Welcome back and welcome to episode 3. Over this series, we have gone from math of attention to big model families. Now comes the part you can use every single day. How do you actually get results out of these models? There are two main ways you can change what you say to the model, that is prompting, or you can change the model itself, that is fine tuning. Today we'll cover both with examples. Let us finish strong. Quick recap. We learned attention and how it powers BERT, GPT and vision transformer. So you understand what is happening under the hood. Today is the practical payoff, and there are two levers you can pull. Lever 1 is prompt engineering. You can change what you say to the model. It is fast, it is free, and it needs no training. Lever 2 is fine tuning. You can change the model itself by training it a little more on your examples. We'll spend first half on prompting and second half on fine tuning. Here is a mental picture that makes all of this click. Think of the model as a brilliant new hire. It knows an enormous amount, but on day one, it doesn't know your goals, your style, or your data. So, how do you get good work out of a talented new teammate? Two ways. You can give them clear instructions. Tell them exactly what you want, maybe with an example, that is prompting, or for something they will do over and over, you can send them to training, let them practice on real examples until it is second nature, that is fine tuning. Say two choices apply to the model. Before we go deeper, one rule of thumb that will save you a lot of time. Always try prompting first. Prompting is fast, free, and easy to undo. Fine tuning costs time, data, and computing power. So climb the ladder in order. Start with a clear prompt. Most tasks are solved right here. If that is not enough, add a few examples inside the prompt. Still not enough? Give the model your own knowledge by feeding it documents when it answers. That is a technique called RAG, and we'll touch on it later. And only if all of that fails short do we reach for fine tuning. Most of the time you will never need that last rung. Let us start with part 1, prompt engineering. That is the craft of asking the right way. Here is the wild part. The same model can give you a brilliant answer or a useless one, and only thing that changed was how you phrased the request. So let us learn how to phrase it well. A strong prompt usually has up to 5 building blocks. A role, who the model should act as. You are a friendly Python tutor. A task, what you actually want done. Explain what this function does. Context, anything the model needs to know. The reader is a beginner, so keep it simple. A format, the shape of the answer. Give me 3 short bullet points, and optionally examples. Show one good answer so it knows the target. You rarely need all 5 at once, but here is the pattern. The more of these you include, the better and more predictable the answer. Technique 1, and most important, be specific, vague in, vague out. Look at weak version, write about dogs. The model has no idea what you want, so you get a generic rambling paragraph. Now the specific version, write 3 friendly tips for first time puppy owners, 1 sentence each. Same model, but now you have told it the topic, the audience, the count, the length, and the tone, and you get back exactly what you pictured. Specific requests are the single biggest upgrade you can make. Technique 2, when describing what you want is hard, just show examples. This is called few shot prompting. Say you want to label reviews. Instead of explaining the rules, you show a couple. Great movie is positive, total waste of time is negative. Then you add it a new one, I loved every minute, and the model copies the pattern and answers positive. The beautiful part, there is no training involved, the example live right inside the prompt. You are teaching by demonstration on the spot. Technique 3 is almost magic for anything with reasoning or math. Ask the model to think step by step. Here is a simple problem. A shop has 24 apples, sells 17, then gets 30 more. How many now? When the model rushes straight to answer, it might blurt 54. It skipped the subtraction, but when you add the words, let us think step by step, it works in stages. Start with 24, sold 17, so 24 minus 17 is 7, got 30 more, so 7 plus 30 is 37, the right answer. Showing the work means each step is easy to check and far fewer mistakes slip through. Technique 4, take control of the output so it comes out predictable every time. Set a role to fix the tone. You are a careful editor. Pin the format, ask for JSON or a table, which is perfect when another program will read the answer. Add constraints under 50 words, no jargon, only use the text I gave you. And give a template, literally show the exact shape you want the answer to follow. The more you remove guesswork, the more consistent results. Before we move on, let us avoid the common traps. Don't ask for too much in one go. Break a big task into smaller prompts. Don't be polite but vague. Maybe help with this is weaker than stating the task directly. If the format matters, don't skip the example. Remember, the model only knows what is in the prompt, so don't forget to give it context and never trust blindly. Always check the facts, numbers, code. A quick review catches the occasional content mistake. Now for the part 2, fine tuning. This is the heavier tool, the one you reach for when prompting truly is not enough. Instead of changing what you say, you change the model itself by training it a little more on examples of your own. Let us see how that works and when it is worth it. Fine tuning is simpler than it sounds. You start with a base model, one that already understands language from all its earlier training. You add your own examples, your label data showing the behavior you want. Then you train, which gently nudges the model internal settings towards your examples, and out comes a tuned model that is now an expert at your specific task. The key idea, you are not starting from scratch, you are standing on the shoulders of a model that already knows language and just adjusting it a little. So you actually have 3 tools, not 2. Let us compare them. Prompting changes your words. It is best for general tasks. It is the cheapest and it needs no data. RAG, which means giving the model right documents at answer time, changes what the model can see. It is best when you need private or up-to-date facts and it needs your documents. Fine-tuning changes the model itself. It is best for a consistent style or a specialized skill. It is the most effort and it needs labeled examples. A good instinct, if the problem is missing knowledge, reach for RAG. If the problem is missing behavior or style, reach for fine-tuning. Now, full fine-tuning, retraining an entire model is heavy and expensive. Most people can't do it on their own machine, but there is a clever shortcut called LoRa. Instead of changing old model, LoRa freezes original weights, leaves them completely untouched, and trains a tiny add-on alongside them. That add-on is often around 1% of model size. You get most of the benefits of fine-tuning for a small fraction of the cost. That is the trick that makes fine-tuning realistic on a single GPU or even a modest laptop. Let us make the prompting side real. Using the pre-Hugging Face library, we load a text generator and then we build a clear structured prompt. Notice the rule, the task and the format all spelled out. We hand it code we want explained and ask the model to continue. Everything we talked about in part 1 in just a few lines. The structure is what makes the answer good. And here is the fine-tuning side, the affordable way. We start from a base model, then within a few lines, we wrap it in small LoRa adapter. When we print the trainable parts, look at the numbers. We are only training about a quarter of 1% of the model. everything else stays frozen. After this, you train it on your examples using a standard trainer. That's a real runnable starting point you could try on a pre-GPU today. And that is the series. Look how far you come in episode 1. Attention, how a model decide what matters. In episode 2, BERT, GPT and vision transformers, one idea, 3 families. And today, prompting and fine-tuning how to get great results from math of attention all the way to a model tuned on your own data. And now you have the full picture. Where to go next? Build a small project end to end. Try RAG over your own notes. Fine tune with LoRa and a pre-GPU, or read the original attention paper. You will understand it now. Thank you for watching the whole series. It really means a lot. If it helped, a like and subscribe go a long way. See you in the next one. Welcome. This is episode 1 of our series on generative models. These are the models that create things. Today we look at 3 big ideas: GANs, VAEs, and diffusion models. They sound complex, they are not. I will explain each one in plain words and I will show you the code. Let us begin. Look at these images. None of them are real. No camera took them. No artist drew them. A computer made them all and it had never seen them before. That feels like magic, but it is not. It is just math we can understand. By end of this video, you will know how it works and you will be able to try it yourself. First, what is a generative model? Most AI does one job. It looks at something and gives it a label. Is this a cat or a dog? Is this email spam? We'll call that telling things apart. Generative models do the opposite. They make new things. You give them a random start. They give you a brand new image. One kind sort, other kind creates. Today is all about second kind. There are 3 main ways to create. The first is GANs. 2 networks compete like a poacher and a detective. They are great at sharp, real-looking images. The second is VAEs. They squeeze data into small code, then build it back. They are great at smooth, tidy results. The third is diffusion. It starts with a noise and cleans it up. It powers most of the today's top image tools. We'll take them one at a time. All 3 share one secret. They learn the shape of the data. Think of all real photos as dots in a space. The model learns where those dots tend to sit. That is the shape. Once it knows the shape, it can pick a new spot. Then it turns that spot into new image. So the trick is simple. Learn the shape, then take a press sample from it. Let us start with GANs. This is the fun one. Picture a poacher and a detective. They are locked in a game and the game makes both of them better. Here is how. A GAN is 2 networks. They have opposite jobs. The first is the generator. It takes random noise and makes a fake image. Think of it as the poacher. The second is discriminator. It looks at image and guesses real or fake. Think of it as the detective. We show the detective real images and fake ones. Its job is to tell them apart. Now the games begin. The generator makes a fake. The detective judges it. If the detective catches the fake, the generator learns from the mistake. Then it tries again a little better and the detective gets sharper too. They push against each other round after round. At first, fakes look rough. Over time, they look real. That back and forth is the whole idea. GANs have clear strength. They make very sharp, real-looking images. They are passed. One pass, you get a picture, and there is a lot of help out there to build them, but they have headaches too. Training can be shaky and hard to control. Sometimes they get lazy and make only a few looks, and it is hard to measure how good they really are. Powerful but tricky. Real world example: creating photorealistic human faces of people who don't actually exist, or generating realistic video game textures. Here is a GAN in code. Don't worry about every line. The generator is just a small network. it takes noise and makes an image. The discriminator is another small network. It takes an image and gives a score, real or fake. Then we train them together. The detective learns to spot fakes. The generator learns to pull the detective. That last line is the key. Its whole goal is to make the detective say real. Next, VAEs. The mood here is comma. The idea is simple. Squeeze the data down to a small, tidy code, then build it back up. And once you can do that, you can create new things too. Let us see how. A VAE has two parts. The first part is the encoder. It takes an image and shrinks it into a small code. The second part is the decoder. It takes the code and rebuilds the image. The clever bit is in the middle. The code is not just one pixel point. It is a small, smooth space. Because it is smooth, we can pick new point in it. Then the decoder turns that point into new image. VAEs have nice strength. Training is calm and steady. The code space is smooth, so you can blend things gently. Picture one place slowly turning into another. The small codes are also useful for other tasks, but there is a cost. The images often come out a bit blurry. They are less sharp than GANs or diffusion, and you have to pick the code size with care. So smooth and stable, but softer. Real world example, photo editing apps that smoothly transition your face from young to old, or changing photos lightning from day to night. Here is the VAE IDN code. The loss has two parts. The first part says rebuild the image well. The second part says keep the code tidy. Both matter. Then we sample a code. We add a little randomness so the model can create, and we pass that code to decoder. The decoder gives us the image back. Two simple goals working together. Now the big one, diffusion. This is the idea behind tools we have actually used. The plan sounds strange at first. Start with pure noise, just static like an old TV. Then slowly turn it into a clear image. Let us see how that works. Diffusion has two directions. First, the forward path. We take a real image, we add a little noise, then a little more. We keep going until it is full static. This part is only used for training. Then comes the reverse path. The model learns to undo each step. It takes noise and removes a little, then a little more. Step by step, an image appears. So the model real job is simple. Look at the noisy image, guess the noise, remove it, repeat. Why did diffusion take over? A few reasons. The quality is stunning. The detail and the variety are the best we have. It is also stable to train. There is no shaky tug of war like in GANs, and it is easy to steer. You can guide with a single text prompt. There is one catch. It is slower because it takes many small steps, but that is getting faster fast. This is the family behind Stable Diffusion, DALI, and Midjourney. Here is diffusion in code. It is shorter than you might expect. We load a ready-made model. We give it a prompt. Here, a cozy cabin in snow forest. We tell it how many steps to take. Then it makes the image and saves it. That's it. And this runs today on a pre-cloud GPU. You can try it right after this video. Let us put all three side by side. GANs work like a poacher and a detective. Their images are sharp, they are fast, but training is tricky. VAs compress and rebuild. They are smooth and stable, but softer and a bit blurry. Diffusion cleans up noise. It has the best quality. It is stable, but it is slower. Pause here and save this. This is the whole video in one table. So what can you do now? You can explain what a generative model really is. You can describe GANs as Porger versus detective game. You can explain how a VAE squeezes and rebuilds data, and you can describe diffusion as cleaning up noise step by step. You can even pick the right tool for a job. Next time in episode 2, we go for the how does a sentence become a picture, that is text to image and multimodal AA. If this helped, give it a like and subscribe for the next one. And tell me in the comments which model you will try first. See you in episode 2. Welcome back. This is episode 2 of our series on generative models. Last time we learned how models create images. Today we learn how to control them. How does typing a sentence give a picture, and how can one model understand both words and images? Let us find out with simple words and real code. You type a sentence. A few seconds later, a picture appears. A picture that never existed before. You didn't draw it, no camera took it, you just described it, and the computer made it. This is text to image. By end of this video, you'll know how it works and you'll learn 3 ways to control it. Quick recap. Last episode, we saw how models create images, GANs, VAEs, and diffusion. But a model that makes random images is not very useful. The real power is control. You want the picture, you have it in your head. So today we cover 3 ways to get it. Part A, text to image, describe it in words. Part B, image to image, start from a picture. Part C, multimodal AA, mix words and images together. First key idea, to turn words into pictures, a model needs both to live in same place. Think of a big space, every idea is a spot. The words, a red bicycle, land at one spot. A photo of red bicycle lands at same spot. They match. A photo of banana lands far away. So the model can tell what fits your words and what doesn't. This shared space is the whole trick. Let us start with part A, text to image. You type a description, you get a picture. Here is what happens in between. The steps are simple. First, your prompt goes into a text encoder. It turns your words into a meaning. Then that meaning guides diffusion model. Remember diffusion from last time? It starts with noise and cleans it up. But now it is not random. Your words steer every step. The result is a picture that matches what you asked for. There is one important dial. It is called guidance. It sets how closely the model follows your words. Turn it low. The model gets creative. It may drift from your prompt. Turn it high. It sticks closely. But too high can look stiff or overbaked. The sweet spot is usual in the middle. Enough to follow you, but still natural. How do you write the prompt really matters? A few simple rules help. First, name the subject. A red box beats an animal. Second, add the style like watercolor, photo, or 3D render. Third, set the scene, the lightning, the place, the mood. Fourth, add few details, but don't pile on too many. Keep it clear, put it together, and you get something like this. A red box reading a book by candlelight, cozy watercolor, warm colors. Here it is in code. We load a ready-made model. We write our prompt. We set the guidance scale. That is the dial we just talked about. We pick how many steps to take. Then the model makes the image and saves it. This is the whole thing, and it runs on pre-cloud GPU. Now part B, image to image. Sometimes you don't start from scratch. You already have a picture, maybe a photo, maybe a rough sketch. Image to image lets you change it. The idea builds on what we know. Normally we start from pure noise. This time we start from your image. We add some noise to it, not all the way, just part way. Then we denoise it, guided by your prompt. There is a knob called strength. Low strength keeps it close to your original. High strength changes a lot. You choose how far to go. This unlocks some fun tricks. In painting, erase part of an image and fill it with something new, like removing a person from a photo. Outpainting, extend a picture beyond its edges, sketch to image, turn a rough drawing into a finished picture, and restyle. Keep the changes but change the whole look. Same tool, 4 different jobs. Here is image to image in code. It is almost same as before. We load the model, we open our input image, we give a prompt and we set the strength. 0 keeps the input, 1 changes it fully, then we get our new image, 1 extra input and a whole new power. Now part C, multimodal AI. So far, what's made images multimodal model go one step further. They handle more than one kind of input at once. What does multimodal mean? Simple. One model that understands different kinds of input together, like an image and a question at the same time. You show it a photo and you ask, what is this? And it answers, a cat and a red sofa. It reads the image and words together, one model, many senses. This unlocks a lot. You can describe a photo, ask what is in this picture, and get a caption. You can answer questions about an image like how many people are there. You can read documents, pull facts from a form or a chart, and some models go further. They can hear and speak too. These are the tools quietly powering a lot of apps you already use. Here is multimodal in code. We load a vision language model, we give it an image and it returns words, a short caption that describes the picture. Notice this is the reverse of text to image. There, words went in and an image came out. Here, an image goes in and words come out. Same simple idea, flip. Let us bring the 3 together. Text to image, you give it words, you get a new image. Image to image, you give it a picture and words, you get a changed image. Multimodal, you give it an image and a question, you get an answer in words. Each one has a key control, guidance, strength, and the prompt you ask. Pause here and save this slide. One honest note before we finish. These tools are powerful and they are easy to misuse. Fake images can fool people. Many models learn from other people's art and data. So check the license before you sell anything you make. A simple rule keeps you safe. Create, don't deceive. So what you can do now? You can explain how words turn into pictures. You can control how literal the model is with guidance. You can edit and restyle images with image to image, and you can describe what multimodal AI is. You can even write better prompts. Next time in episode 3, we get a practical real case study how marketing team use generative AI, the wins and the pitfalls. If this helped, give it a like and subscribe and tell me in the comments what will you create first. See you in episode 3. Welcome to episode 3 and it is a fun one. We have learned how AI create images. We have learned how to control it. Now let us see it work in real world. This is a marketing case study. We look at how a tiny team used generative AI to run their marketing, the playbook, the results, and the honest pitfalls. Let us dive in. Here is a true to life story. A 3-person team, they made a whole month of marketing content in a single weekend, 60 plus social and ad assets, 1 weekend, not a month, and $0 on a photo shoot. How did they do it? Let us break down exactly what they did and what you can copy. First, why this matters so much. Marketing runs on content, post, ads, emails, images, and content has always been the bottleneck. It is slow to make and it is expensive. Generative AI changes that math. Slow becomes fast, drops appears in seconds, not days. Costly becomes cheap, fewer shoots, fewer agencies, less stock, and few becomes many. You can make endless versions to test. The hard part was never ideas, it was making the stuff. That is what AI removes. Let us meet our example. We call them Brew and Blue, a small coffee brand that sells online. Just 3 people, a tight budget, but big plans. They live and die by social media and ads, and they hit 3 walls. A tiny team with no designer or photographer, a small budget, so no agencies, and constant demand because social never stops. Quick note, this is a composite example. It is typical of small brands today. So the number letters are representatives, not one's company's exact figures. So here was the job to be done. 1. A month of social post for Instagram and TikTok, several a week. 2. Add creatives to test, many versions, not just one. 3. Brush product images without booking a studio. And 4. Emails and captions, inconsistent voice, written past. That is a lot for 3 people. Let us see how AI helped. Part A, the playbook. Here is exactly how they used generative AI step by step. First, a map. They didn't use AI for just one thing. They went through almost everything: social images, captions and copy, email flows, ad creatives, product markups, even a short video. One tool, many jobs. That is the mindset shift, not a single trick, a helper across the whole workflow. But here is the real secret. It is not let AI do it all. It was a simple pipeline with a human at the controls. It goes like this. Start with a brief. What do we need and why? Then write a prompt. Describe it clearly. Then generate. The AI makes a drop. Then the key step. A human reviews and edits. That is where the real magic happens. And finally publish. AI drops fast, but a person has the final say. That is what protects quality and brand. Now let us look at the first use case. Product and lifestyle images. No studio required. Here is the trick. They took a plain product photo, just a phone shot. Then they used image to image and dropped it into rich on-brand scenes. A cozy morning, a summer picnic, a holiday table. What is the win? Dozens of seasonal looks from one photo, new scenes for every holiday with no reshoot. One tip, keep the products itself unchanged, only let AI build the background. Use case 2, ad variants at scale. Normally you make one ad and you hope it works. Instead, they made many different headlines, different scenes, different angles, cozy, gift, summer, one base idea, many spins. Then they let the data decide. They ran them as test and kept what performed, and it was cheap to try. Testing 20 ideas cost almost nothing. This is how a small brand can beat a big budget. Cheap testing wins. Use case 3, captions, copy and email. Writing is slow when you stare at blank page, so they let AI write the first draft. Here is a prompt they used. Write 3 Instagram captions for our cold brew, friendly, under 20 words, with a question and 2 emojis. And in second, they got options like mornings just got smoother, what is feeling your day. Then a human picks the best one and tweak the voice. Dropped in seconds, polish in a minute. The AI gives the first draft, never the final word. For the coders watching, here is a bonus. You can bash this in a few lines. We load a text generator, we pick a product and a list of angles. Then we loop. For each angle, we ask for a caption. One short loop turns a single idea into a whole batch. That is how scale really happens. And if you don't code, no worries. The idea is what matters. One input, many outputs. Part B, the results. So what actually happened? Let us look at the numbers. Here is the before and after. 5 times more content per month, cost per asset down about 70%, campaign turnaround from 2 weeks to 2 days, and ad engagement of 38%. Why the lift? Because they could finally test lots of ideas. Again, these are representative figures, typical of small teams adapting these tools. But the direction is real, more, faster, and cheaper. Let us make it concrete. Day to day, what changed? Making a product image before book a shoot, wait days, after minutes from a phone photo. Add creatives for test before 1 or 2, too costly, after 10 to 20. Writing captions before hours of starring, after a dropped in seconds, then edit. And who does it? Before I wrote or just skip it, after the 3% team in-house, same team for more output. Now part C, the pitfalls. This is the honest part because it does go wrong. Let us talk about where and how they avoided it. Here are the risks to watch. First, AI look, generic, same images that feel of brand. Second, brand dip, your voice and colors wander without a guide. Third, licensing and rights. Can you actually use it commercially? Check. Fourth, mistakes and made up facts. AI text can be confidently wrong. And fifth, disclosure and trust. Hiding AI use can backfire with customers. None of these are reasons to avoid AI, they are reasons to use it carefully. So, here are the guardrails that worked. 1. A human in the loop. Every asset gets a human review before it ships. 2. A brand kit in the prompt, same colors, fonts, and voice every time. 3. Check the license, know your rights before anything goes commercial. And 4. Be honest about AI, disclose where it matters, keep customer trust. Notice something, each guardrail picks a risk from last slide, match them up. And finally, when not to lean on AI, humans still matter, real people and real claims. Testimonials, paces, and packs must be true. Your core brand moments, a signature campaign deserves a human touch. Anything sensitive or legal, health, finance, safety, get it checked. And when good enough just is not. Sometimes a real photographer wins. AI is a power tool, not autopilot. The brands that win keep a human in charge. And that is the world generative models. Let us look back. Episode 1, how AI creates GANs, VAEs, and diffusion. Episode 2, how to control it, text and image generation. And episode 3, how it is used, real marketing end to end. You know how generative AI works, how to steer it, and how real teams put it to work responsibly. So here is your turn. Pick one task and try AI this week. Make 10 AD variations and test them. Build a simple brand kit prompt and always keep a human in the loop. Thank you for watching. It really means a lot. If it helped, a like and subscribe go a long way. See you soon.